Hello and welcome to the Drift to the Stars. I'm glad you're here tonight. Maybe it's been a long day. Maybe your thoughts are still moving too fast, still carrying the weight of everything that happened between morning and now. Or maybe you're simply the kind of person who finds it easier to let go when there's something quiet and vast to drift toward. Either way, this is for you. You don't need to do anything right now except rest. Let your breath slow. Let your shoulders soften. Let your body grow heavy against whatever is holding you, and imagine, just for a moment, that gravity has loosened its grip, that you've begun to float gently and without effort out into the dark. Because tonight, we're going to drift through the solar system together. Not in a hurry, not in a straight line, but in slow, soft spirals, from sun-warmed planets and dusty rings to shadowed craters and frozen oceans sealed beneath ancient ice. We'll move through magnetic storms and tilted axes, past moons that glow and worlds that roll. From sideways planets and diamond rain to ancient lights still crossing the void, every orbit holds something worth pausing over. We'll go slowly, one quiet fact at a time. And just before we begin, if these gentle explorations help you unwind or give you a peaceful way to close your day, consider tapping the like button and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. We'll start at the edge. Far from the sun, in the cold blue outer reaches of the solar system, lies Neptune, the most distant of the 8 known planets. You might expect a world so far from its star to be still, frozen, quiet. But Neptune is none of those things. Despite receiving only a fraction of the sunlight that warms our own world, Neptune hosts the fastest winds in the entire solar system. They tear through its upper atmosphere at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth, faster than any storm our own planet has ever produced. These winds are not driven by sunlight. They rise from within. Neptune radiates its own internal heat outward through its layers, and it is this energy, ancient leftover warmth from the planet's formation, that powers the perpetual howling in its clouds. The atmosphere itself is mostly hydrogen, helium, and methane. That methane is what gives Neptune its deep, pale blue color. And across those blue clouds, invisible to us, supersonic winds carve and reshape the planet's face in constant, silent motion. A frozen world, in perpetual supersonic storm. Mars is a world of geological extremes, and nowhere is that more apparent than along its equator, where the land simply opens. Valles Marineris is the largest canyon system in the solar system. It stretches more than 4,000 kilometers across the Martian surface, a distance wide enough to span the entire continental United States. In its deepest reaches, it plunges more than 7 kilometers down. That is more than 5 times the depth of the Grand Canyon. Unlike Earth's Great Canyons, which are carved slowly by rivers over millions of years, Valles Marineris likely formed through a different kind of violence. As Mars cooled and its crust contracted, the surface cracked and pulled apart. Volcanic activity widened those cracks further. Erosion shaped the edges over time. The result is a wound in the Martian landscape so vast it can be seen from space with the naked eye. A scar that hints at a turbulent geological past, now frozen, now still, now silent beneath a pale pink sky. Venus is in many ways Earth's twin. It is nearly identical in size, in mass, in the rocky composition of its interior. For a long time, scientists wondered if it might even be habitable, a second Earth wrapped in clouds. But Venus is missing something crucial, something invisible and yet essential. Unlike Earth, Venus has no global magnetic field. On our planet, this field is generated by the slow churning of molten iron deep within the outer core, a natural dynamo that wraps the entire world in a protective magnetic bubble. Venus, however, appears to have a core that is either too sluggish or too solid to produce the same effect. Without that shield, the solar wind strikes Venus's atmosphere directly. Over billions of years, this constant bombardment has stripped away lighter elements, gradually eroding what the planet once had. Some scientists believe Venus may have been far more Earth-like in its distant past, perhaps even cool enough for liquid water. The absence of a magnetic field may be part of what ended that chapter. A slow, invisible undoing, written in the movement of charged particles across deep time. Far out in the cold darkness, where sunlight arrives as little more than a faint glimmer, Uranus and Neptune hold their secrets under immense pressure. Deep within their thick atmospheres, something extraordinary may be happening. It may be raining diamonds. These two planets carry dense layers of methane gas in their interiors. Under the right conditions, extreme heat, crushing pressure, that methane can break apart. The carbon atoms it releases are compressed, forced together, restructured into crystalline form. Tiny diamonds, formed in darkness, that slowly drift downward through the planet's interior toward the core. Scientists have simulated this process in laboratories, subjecting hydrocarbons to pressures that mimic the deep interiors of these distant worlds. The results support the theory. Under those conditions, carbon does indeed compress into diamond. If the model is correct, then somewhere in the blue-black depths of Neptune and Uranus, storms of glittering crystals fall in silence through layers of gas no human eye has ever seen. Not rain as we know it, but something quieter, stranger, and in its own way, more beautiful. Beneath your feet right now, the ground is moving. Not quickly. Not in any way you could feel from moment to moment. But over millions of years, the surface of our planet is in constant slow motion, carried along on a network of massive crustal plates that drift across the molten mantle below. This is plate tectonics. And as far as we know, Earth is the only planet in the solar system that has it. These shifting plates do more than create earthquakes and raise mountains. They drive the long-term carbon cycle, pulling carbon dioxide from the atmosphere, locking it into rock, and eventually releasing it again through volcanic activity. This process has helped regulate Earth's climate over geological timescales, keeping conditions stable enough for life to persist. Mars and Venus both show signs of ancient volcanic activity and surface fracturing. But they appear geologically stagnant now, their crusts fixed in place, their interiors no longer driving the kind of planetary recycling that Earth sustains. It may be that plate tectonics is not just a feature of our world, but one of the reasons it remains livable. A slow, grinding engine running just below the surface, keeping the planet breathing across deep time. When we picture asteroids, we tend to imagine solitary objects, lone rocks tumbling through the void, silent and companionless. But some of them are not alone. Some asteroids have moons. The first confirmed example was discovered in 1993, when the Galileo spacecraft passed through the asteroid belt on its way to Jupiter. Among its observations was something unexpected, a small rocky body called Dactyl, orbiting the larger asteroid Ida. It was the first time a natural satellite had been confirmed around an asteroid. Since then, dozens more have been found. Some asteroids have two moons. Some exist in binary arrangements, where two similarly sized objects orbit each other in a slow gravitational embrace. The same compound responsible for rust. Mars's surface rocks are rich in iron. Over billions of years, that iron has oxidized, reacting with oxygen in the thin Martian atmosphere and with water that once flowed across the surface. producing iron oxide dust that covers the planet in a fine, pervasive layer. This dust is extraordinarily light. It is carried by the Martian wind, suspended in the atmosphere during storms, and deposited across every surface on the planet. The dust colors not just the ground, but the sky. On a clear day on Mars, the sky is not blue, but a pale butterscotch. Sunlight scattered by iron oxide particles suspended in the thin air. During global dust storms, the sky deepens to a dark reddish-brown, and the sun becomes a pale smear of light barely visible through the haze. Beneath the rust, Mars has other colors. Dark basaltic plains of volcanic rock. These tiny systems form through capture, through collision, or through co-formation from the same ancient cloud of debris. White polar ice caps. The pale beige of ancient windswept dunes. But from a distance, from space, from Earth, the iron oxide dominates. A planet wearing its geological history on its surface, reddened by billions of years of slow oxidation, marked permanently by the chemistry of its own past. The sun's surface appears in casual observation, uniform and featureless, a blazing disk of white-yellow light, steady and unchanging. But it is not uniform, and it is not unchanged. Scattered across the photosphere, appearing and disappearing over days and weeks, are sunspots, regions where the surface appears distinctly darker than the surrounding area. They are not cold in any ordinary sense. A sunspot's temperature is typically around 3,500 degrees Celsius. What they reveal is something quietly profound. It only appears dark because the surrounding photosphere burns at 5,500 degrees, and the contrast makes the cooler region look shadowed by comparison. Sunspots form where intense concentrations of magnetic field lines pierce the surface of the sun. These magnetic structures suppress the normal convective flow of hot plasma rising from the interior, blocking the upward transport of energy and producing a region that is cooler and less luminous than its surroundings. The magnetic field lines that create sunspots are twisted and stressed, storing enormous amounts of energy that can be released suddenly as solar flares or coronal mass ejections. Sunspots appear in cycles. At solar minimum, the surface may be almost entirely clear of them. As the solar cycle progresses towards solar maximum, they multiply, appearing in pairs and clusters, sometimes growing to sizes larger than Earth. They are temporary features, each one lasting from days to months before dispersing back into the surrounding photosphere. The sun's surface is not a steady, passive source of light. It is a magnetically active environment, marked by scars that appear, evolve, and vanish, recording the internal dynamics of a star that is never entirely at rest. For most of human history, the solar system had 6 known members beyond the Sun: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Gravity does not only bind planets to stars or moons to planets. These were the planets visible to the naked eye, known to every civilization that looked up at the night sky. Tracked across the heavens by Babylonian astronomers, Greek philosophers, and medieval scholars alike. Then, on the 13th of March 1781, an amateur astronomer in Bath, England, pointed a homemade telescope at a faint point of light and noticed something unusual. William Herschel was conducting a systematic survey of the sky when he observed an object that appeared slightly different from the stars around it. Over subsequent nights, he watched it move, slowly, deliberately, against the fixed background of stars. Stars do not move like that. Planets do. Herschel initially believed he had discovered a comet. But as more observations accumulated and the object's orbit was calculated, the truth became clear. It was a planet, a new planet, orbiting the Sun beyond Saturn at a distance no human had previously known to explore. Uranus became the first planet discovered in the modern era, and the first found through the use of a telescope rather than the naked eye. It reaches down to the smallest scales, linking fragments of rock in the dark, keeping them together across millions of years of drifting silence. Its discovery immediately doubled the known radius of the solar system, pushing the boundary of the planetary region from Saturn's orbit outward into previously unmapped space. It was a moment that changed not just astronomy, but the way humanity thought about the extent of the solar system itself. The edge, it turned out, was farther than anyone had imagined. And beyond Uranus, as later discoveries would show, there was still more. Everything in the solar system, the sun, the planets, the moons, the asteroids, the comets, the dust, emerged from the same source. Approximately 4.6 billion years ago, a vast cloud of gas and dust drifting through the Milky Way began to collapse under its own gravity. The trigger may have been a nearby supernova, a shockwave from an exploding star compressing the cloud past the point at which its own internal pressure could resist. Once the collapse began, it accelerated. Material fell inward, the cloud began to rotate, and at its center a dense, hot core formed. That core became the sun. The remaining material, the gas and dust that did not fall into the center, flattened into a rotating disk around the young star. Even wanderers, it seems, can find companions. Within that disk, particles collided and stuck together, gradually accumulating into larger and larger bodies through a process called accretion. Pebbles became boulders. Boulders became planetesimals. Planetesimals collided and merged into protoplanets. Over tens of millions of years, those protoplanets grew into the planets we know today. The process was not orderly. It was chaotic, punctuated by enormous collisions, gravitational migrations, and the bombardment of the inner solar system by material from the outer regions. The solar system we inhabit now is the survivor of that chaos. The stable arrangement of today is what remains after billions of years of collisions, ejections, and gradual settling. Everything around us is 4.6 billion years old. Mercury is the smallest planet in the solar system and the closest to the sun. You might expect it to have a thick atmosphere, pressed down by solar energy and held in place by proximity to such an enormous source of heat. The ground beneath your feet, the air above you, the light crossing the sky, all of it assembled slowly from the same ancient cloud. In the asteroid belt, most objects are undifferentiated, composed of roughly the same material throughout, never having been large enough or hot enough for gravity and heat to separate their components into distinct layers. Vesta is an exception. The second largest object in the asteroid belt, with a diameter of approximately 525 kilometers, Vesta is large enough to have undergone a process called planetary differentiation early in its history. Shortly after its formation, the young Vesta generated sufficient internal heat from the decay of short-lived radioactive isotopes to melt its interior. Denser materials, primarily iron and nickel, sank toward the center, forming a metallic core. Lighter silicate materials rose toward the surface, forming a crust and mantle. But Mercury has almost nothing. This is the same layered structure found in Earth, Mars, and the other terrestrial planets. Vesta, despite never having grown to planetary size, went through the same internal sorting process. It is, in the language of planetary science, a protoplanet, a body that began the journey toward becoming a full planet, but was halted, most likely by Jupiter's gravitational influence preventing further accretion in the asteroid belt. The Dawn spacecraft, which orbited Vesta from 2011 to 2012, revealed an enormous impact crater at the South Pole, the Ria Silvia Basin, so large and deep that it exposed material from Vesta's interior. Rocky fragments ejected by that ancient impact have been identified among meteorites found on Earth, giving scientists direct physical samples of a differentiated asteroid. Vesta is a fossil of planetary formation, a world that almost was. The moon appears from Earth as the very image of stillness. Its face barely changes from one human generation to the next. Its craters, its plains, its mountain ranges have looked essentially the same for billions of years. What surrounds it is not an atmosphere in any meaningful sense. It is the most unchanging landscape most of us will ever observe. But the moon is not entirely still. Seismometers placed on the lunar surface by Apollo mission astronauts between 1969 and 1972 detected something unexpected. The moon shakes. Moonquakes occur regularly, generated by several different mechanisms. Some are caused by the gravitational tidal forces exerted by Earth, which flex the lunar interior as the moon moves through its elliptical orbit. Some are triggered by the thermal expansion and contraction of surface rocks as they pass from the extreme cold of lunar night to the intense heat of lunar day. Some result from meteorite impacts, and some originate deep within the moon's interior for reasons not yet fully understood. Unlike earthquakes, which typically last seconds to minutes and then fade, deep moonquakes can continue for up to an hour, a consequence of the moon's dry, cold, rigid interior, which allows seismic waves to reverberate with very little attenuation. The Apollo seismic network operated until 1977, and the data it collected continues to be analyzed. It is an exosphere, a near vacuum so thin that the particles within it almost never collide with one another. What it revealed is a moon with an interior that, while far less active than Earth's, is not dormant. Something moves within it. Something shifts and rings and eventually settles back into silence. Neptune orbits the Sun at an average distance of approximately 4.5 billion kilometers, so far away that sunlight takes over 4 hours to reach it. It is a cold, remote world at the outermost edge of the planetary solar system. And around it, in orbits ranging from close and circular to distant and wildly irregular, move at least 14 known moons. Triton dominates the system. It accounts for more than 99% of the total mass orbiting Neptune, and its retrograde orbit, moving opposite to Neptune's rotation, sets it apart from every other large moon in the solar system. Its captured origin likely disrupted whatever satellite system Neptune originally possessed, scattering smaller moons into unstable orbits or ejecting them entirely. What remains beyond Triton is a collection of smaller, darker bodies. They simply bounce. Proteus, the second largest, is an irregular, heavily cratered object orbiting close to Neptune. Nereid follows an unusually elongated orbit, one of the most eccentric of any moon in the solar system, suggesting it may have been gravitationally perturbed by the same event that captured Triton. Several smaller inner moons orbit within Neptune's ring system, their gravity influencing the ring structure around them. The outer moons, small, dark, and irregularly shaped, orbit at great distances and in varied inclinations. Many of them almost certainly captured Kuiper belt objects drawn in by Neptune's gravity over billions of years. Together they form a sparse, scattered family, shaped by capture, disruption, and the long, slow influence of gravitational forces acting across deep time. For as long as humans have studied the Sun, we have studied it from a distance. Telescopes on the ground, instruments in Earth orbit, spacecraft observing from millions of kilometers away, all of them gathering data across space, separated from their subject by the vast and lethal gulf between. In 2018, that changed. NASA's Parker Solar Probe launched on a trajectory that would take it closer to the Sun than any spacecraft in history. Over a series of increasingly close orbits, using Venus's gravity to gradually reduce its perihelion distance with each pass, Parker has approached the Sun to within a few million kilometers of its surface. Well within the outer corona, the Sun's extended outer atmosphere, atoms of sodium, potassium, and oxygen, blasted loose from the surface by the constant impact of solar wind particles and micrometeorites, drift briefly above the ground before escaping into space. In December 2021, Parker became the first spacecraft to fly through the corona itself. Dipping below the Alphen critical surface, the boundary beyond which solar material is gravitationally and magnetically bound to the Sun, for the first time, a human-made object was, technically, touching the Sun. The probe travels at speeds exceeding 690,000 kilometers per hour at closest approach, the fastest any human-made object has ever moved. Its carbon composite heat shield, just 11.5 centimeters thick, maintains the instruments behind it at room temperature, while its sun-facing side endures temperatures exceeding 1300 degrees Celsius. The data Parker is returning is already reshaping our understanding of solar wind acceleration, coronal heating, and the magnetic structures that drive space weather. Questions that have persisted for decades are beginning, slowly, to yield answers. A spacecraft built by human hands, flying through the atmosphere of a star. Among the meteorites that have been collected on Earth, fragments of asteroids and other solar system bodies that survived their passage through the atmosphere and landed on the surface, a small and distinctive subset came from somewhere much more specific. They came from Mars. These Martian meteorites, around 300 have been identified so far, were blasted off the Martian surface by large asteroid impacts billions, or in some cases millions, of years ago. The force of those impacts was sufficient to accelerate fragments of Martian crust to escape velocity, sending them into space on trajectories that eventually, after journeys lasting millions of years, brought them into Earth's path. Because Mercury's gravity is too weak to hold these particles for long, they are constantly lost and constantly replenished. Scientists identify them through their chemical and isotopic composition, which matches the data returned by Mars rovers and orbiters with remarkable precision. Some contain tiny bubbles of gas whose composition matches the Martian atmosphere as measured directly by spacecraft. Some show evidence of having formed in the presence of liquid water, minerals and textures that could only have developed in a wet environment. One Martian meteorite, found in Antarctica and designated ALH-84-1, generated significant scientific and public interest in the 1990s, when researchers proposed that certain structures within it might be evidence of ancient microbial life. That claim remains contested, and no consensus has been reached. But the meteorite and the debate it sparked highlighted what these wayward rocks represent: direct physical samples of another planet, delivered to Earth free of charge by the violence of ancient impacts. Of all the objects in the solar system, the Sun is by far the largest, the most massive, and the most energetically significant. It is also, in terms of its elemental composition, remarkably simple. The surface gives up a little of itself every day, and the solar wind carries it away. Approximately 73% of the Sun's mass is hydrogen. Nearly all of the remaining 27% is helium. Everything else, oxygen, carbon, nitrogen, silicon, iron, and all the other elements detectable in the solar spectrum, makes up roughly 2% of the total. Hydrogen and helium are the two lightest and most abundant elements in the universe, produced in the first few minutes after the Big Bang. The Sun, like most stars, is composed overwhelmingly of these primordial materials, the same elements that dominated the universe long before any planet, any rock, or any heavier element existed. The heavier elements present in the Sun, and in the planets, and in our own bodies, were not created in the Big Bang. They were forged in the cores of earlier generations of stars, scattered into space when those stars ended their lives, and incorporated into the cloud of material that eventually collapsed to form our solar system. The carbon in your cells, the iron in your blood, the oxygen in the air you are breathing right now. The result is a ghostly, shifting envelope, invisible to the eye, detectable only with sensitive instruments. All of it was produced inside a star that died before the sun was born. The sun burns hydrogen into helium, as it has for 4.5 billion years. In doing so, it continues a process of stellar nucleosynthesis that connects every atom in the solar system to the broader history of the universe itself. Earth's axis is not perpendicular to its orbital plane. It leans, tilted at approximately 23.5 degrees relative to the plane in which it orbits the sun. This tilt is constant in direction, pointing toward the same region of space throughout the year, toward the North Star, Polaris, as Earth moves around the sun. This fixed tilt is the reason seasons exist. In June, the northern hemisphere is tilted toward the sun. Sunlight strikes it at a more direct angle, and days are longer. More energy reaches the surface per unit area, temperatures rise, and summer follows. Meanwhile, the southern hemisphere is tilted away, receiving sunlight at a shallower angle, experiencing shorter days and cooler temperatures, winter. In December, the geometry reverses. The southern hemisphere tilts toward the sun, and the northern hemisphere tilts away. Not a sky exactly. 6 months later, the cycle completes. At the equinoxes, around March and September, neither hemisphere is tilted significantly toward or away from the sun. Day and night are approximately equal in length across the planet, and the transition between seasons is at its midpoint. Without Earth's axial tilt, this seasonal rhythm would not exist. The sun would trace the same path across the sky every day of the year. Temperatures at any given location would remain nearly constant across the calendar. The ecological cycles driven by seasons, migration, hibernation, flowering, breeding, would be entirely different or would not exist at all. A 23.5-degree lean. And from that lean, the entire seasonal architecture of life on Earth. Jupiter's magnetic field is the largest planetary structure in the solar system. It extends approximately 700,000 kilometers toward the sun and stretches in the opposite direction, away from the sun in the magnetic tail, for hundreds of millions of kilometers, reaching as far as the orbit of Saturn. More like a whisper. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear several times larger than the full moon in the night sky. The field is generated by electric currents flowing through Jupiter's interior, specifically through a layer of hydrogen compressed to such extreme pressures that it transitions into a metallic state, conducting electricity like a metal despite remaining a fluid. This metallic hydrogen layer, churning under the influence of Jupiter's rapid rotation, produces a magnetic dynamo far more powerful than the one inside Earth. Within the magnetosphere, charged particles, many of them originating from volcanic eruptions on Io, are trapped and accelerated to enormous energies, forming radiation belts of extraordinary intensity. These belts pose significant hazards to spacecraft, and mission designers must carefully plan trajectories that minimize exposure time in the most dangerous regions. The magnetosphere also produces the most powerful auroras in the solar system, vast persistent rings of ultraviolet and X-ray emission at Jupiter's poles, hundreds of times more energetic than Earth's own auroral displays. Jupiter's magnetosphere is invisible, lethal in places, and vast beyond easy comprehension. It is, in terms of sheer scale, the largest coherent structure that any planet in the solar system produces. Saturn's rings are the most famous. But Saturn is not the only ringed planet in the solar system. A faint shimmer of scattered atoms clinging briefly to a world that cannot quite hold them. Jupiter, Uranus, and Neptune all possess ring systems of their own, fainter, darker, and less dramatic than Saturn's, but present nonetheless. And none of them will last forever. Planetary rings form through several mechanisms. A moon venturing too close to its host planet may be torn apart by tidal forces once it crosses the Roche limit, the boundary within which gravitational stress exceeds the structural strength holding the moon together. A collision between moons or between a moon and an impacting body can scatter debris into orbit. Material left over from the planet's formation may never have coalesced into a moon at all, remaining instead as a diffuse ring of particles. But the same gravitational forces that create rings also work over time to destroy them. Particles at the inner edge of a ring system gradually lose energy to atmospheric drag or magnetic interactions and spiral inward, falling onto the planet below. Particles at the outer edge can be nudged outward by gravitational resonances and eventually escape the ring system entirely. Saturn's rings, as the Cassini mission revealed, may be less than 100 million years old, formed recently in planetary terms, and already being depleted at a measurable rate. At the center of everything, the sun is burning. At current rates of loss, they may be gone within a few 100 million years. The rings we see today are not a permanent feature of the solar system. They are a phase, a transient arrangement of ice and dust, beautiful and temporary, existing in the brief window of time when the conditions for their formation and persistence happen to coincide. We are fortunate to be here while they still exist. On Earth, the past is constantly being erased. Rain weathers rock. Rivers carry sediment. Glaciers grind down mountains. Tectonic plates subduct ancient crust back into the mantle. Volcanic eruptions bury old surfaces under new material. Every second, more than 4 million tons of the sun's own mass is converted into energy through nuclear fusion. The biological activity of billions of organisms chemically alters soil and atmosphere. Earth is a planet that continuously overwrites its own history. The moon does none of this. Without an atmosphere, there is no wind, no rain, no weathering in the terrestrial sense. Without active geology, there are no eruptions to resurface the terrain, no tectonic movements to fold and deform the crust. Without liquid water, there is no erosion, no sediment transport, no chemical alteration of exposed rock. The principal agents of change on the moon are micrometeorite impacts, tiny particles striking the surface continuously, slowly churning and grinding the uppermost layer of rock into a fine powder called regolith, and the thermal cycling of the surface between the extreme cold of lunar night and the intense heat of lunar day, which gradually fractures surface rocks over long timescales. These processes are real, but they are slow, extraordinarily slow. Craters formed billions of years ago remain essentially intact. In the crushing heat and pressure of the solar core, hydrogen atoms are forced together until they merge into helium. And in that merging, a small amount of mass disappears entirely, transformed into the light and heat that powers our entire solar system. The footprints left by Apollo astronauts in the lunar regolith will persist, undisturbed for millions of years. The moon is a geological archive, a record of the solar system's early history preserved in the absence of the forces that would otherwise erase it. Every crater on its surface is a timestamp. Every ancient highland a fragment of a world that formed 4.5 billion years ago and has barely changed since. On Earth's ocean floor, in complete darkness, under crushing pressure, far from sunlight, entire ecosystems thrive. They are built not around photosynthesis, but around chemosynthesis, the ability of certain microorganisms to extract energy from chemical reactions involving minerals and heated water venting from the sea floor. These hydrothermal vent communities support a remarkable diversity of life, from specialized bacteria to tube worms, shrimp and fish, all sustained by the chemical energy flowing upward from beneath the crust. The significance of this, in the context of the solar system, is profound. If life on Earth can exist in total darkness, sustained by chemical energy alone, without any connection to sunlight, then the requirement for a planet to orbit in its star's habitable zone, the region where liquid water can exist on the surface, becomes less absolute. Life might exist wherever liquid water contacts warm rock. That energy radiates outward in all directions. And in the outer solar system, that condition may be met in several places. Beneath the ice of Europa, a subsurface ocean is believed to be in contact with a rocky seafloor. Tidal heating from Jupiter keeps the ocean liquid and may drive hydrothermal activity at the ocean floor. The Cassini spacecraft detected molecular hydrogen in the plumes of Enceladus, a chemical signature consistent with ongoing hydrothermal reactions between water and rock. These detections do not confirm life. They confirm the presence of conditions under which life, as we understand it, could potentially exist. The most promising places to search for biology beyond Earth may not be warm, sunlit planets. They may be cold, dark, ice-covered moons, lit from within by the slow friction of gravity. The light that reaches Earth from the Sun has traveled approximately 150 million kilometers to get here. At the speed of light, approximately 300,000 kilometers per second, that journey takes just over 8 minutes. It warms our oceans, drives our winds, and makes photosynthesis possible. When you see the sun in the sky, you are not seeing it as it is at this moment. You are seeing it as it was 8 minutes ago. The sun you observe is the sun of the recent past, its light already old by the time it reaches your eyes. But that 8-minute journey is only the final easy leg of a much longer trip. The energy that arrives as sunlight began its existence in the sun's core, generated by nuclear fusion under conditions of extreme heat and pressure. But a photon produced in the core does not travel directly outward. The interior of the sun is so dense that light cannot travel freely through it. It is immediately absorbed by the surrounding plasma and re-emitted in a random direction, then absorbed again and re-emitted again in a process that repeats an almost incomprehensible number of times. This random walk through the solar interior, a process called radiative diffusion, means that the energy produced in the core takes an extraordinarily long time to work its way outward. Estimates vary, but the journey from the core to the surface may take anywhere from 10,000 to 100,000 years. The warmth reaching your skin on a clear afternoon was generated inside the sun long before recorded human history began. Every living thing on Earth depends in some way on that continuous act of self-consumption happening 93 million miles away. It spent thousands of years making its way slowly outward through layers of dense plasma, and then crossed 150 million kilometers of empty space in just over 8 minutes. Ancient energy arriving fresh. Europa's surface is unlike almost anything else in the solar system. It is smooth, smoother than almost any other solid body we have observed, with very few impact craters, suggesting a surface that has been geologically renewed relatively recently. But it is not featureless. It is covered in a dense, complex network of dark lines, ridges and bands that crisscross in all directions, overlapping and intersecting in patterns that record a long history of surface deformation. These features suggest that Europa's ice shell is not static. It moves. The leading model describes an ice shell perhaps 10 to 30 kilometers thick, floating on the liquid ocean below, subject to the continuous tidal flexing caused by Jupiter's gravity. This flexing causes the ice to crack, shift, and refreeze in new configurations, a process that bears a striking resemblance, in its mechanics, if not its materials, to the plate tectonic processes that reshape Earth's surface. The loss measured against the Sun's total mass is almost imperceptible. In some regions, called chaos terrain, the surface appears to have broken into separate plates of ice that shifted, rotated, and refroze in new positions, like a jigsaw puzzle that has been disturbed and incompletely reassembled. Scientists studying these regions have proposed that surface ice may sometimes be subducted back into the ocean below, while fresh ice rises to replace it. If this model is correct, Europa would be the only body in the solar system other than Earth known to have an active plate-like recycling process. And that recycling may be significant, cycling nutrients and oxidants from the irradiated surface down into the ocean, potentially enriching it with the chemical ingredients that biology requires. A frozen surface, a moving shell, an ocean below waiting. Saturn is the second largest planet in the solar system, with a volume more than 700 times that of Earth. It is a world of extraordinary scale, its equatorial diameter nearly 10 times Earth's, its mass approximately 95 times greater. And yet, despite all of that size and mass, Saturn is remarkably light. It will take billions of years before the Sun exhausts its hydrogen supply. Its average density is approximately 687 kilograms per cubic meter. The density of water is 1,000 kilograms per cubic meter. Saturn, on average, is less dense than water, meaning that if a body of water large enough to contain it could somehow exist, Saturn would float. This seems counterintuitive for a planet of such enormous mass. But Saturn is composed overwhelmingly of hydrogen and helium, the lightest elements in the universe, with no solid surface and a relatively diffuse internal structure. Its core, though dense, is small relative to the planet's total volume. Most of Saturn's bulk is simply very light gas, compressed by gravity, but still far less dense than the rocky and metallic materials that give the terrestrial planets their heft. Saturn's low density also contributes to its shape. Because it is so light and spins so rapidly, completing a full rotation in just over 10 hours, the centrifugal effect of that rotation causes the planet to bulge significantly at its equator and flatten at its poles. Saturn is the most oblate planet in the solar system, noticeably non-spherical even in images taken through modest telescopes. For now, it burns with extraordinary steadiness, a controlled, continuous sacrifice, a star slowly spending itself so that everything around it can exist. A giant world, light enough to drift on water, spinning fast enough to visibly flatten itself, and still somehow the most recognizable planet in the solar system. The Sun is not a stable, unchanging source of light and warmth. It is a dynamic, magnetically active star, and periodically it releases energy in sudden, powerful bursts that can be felt across the solar system. Solar flares are among the most energetic events in the solar system. Sudden releases of electromagnetic radiation from regions of the Sun's surface where magnetic field lines have become twisted, stressed, and then suddenly reconnect in a process called magnetic reconnection. In a matter of minutes, a solar flare can release energy equivalent to billions of nuclear weapons, emitting intense bursts of X-rays, ultraviolet radiation, and radio waves across the electromagnetic spectrum. When a flare is directed toward Earth, the radiation arrives in approximately 8 minutes, the same travel time as ordinary sunlight. Upon reaching Earth, it interacts with the upper atmosphere, ionizing gases in the ionosphere and disrupting the radio wave propagation that underpins long-distance communication, GPS signals, and aviation navigation systems. Often accompanying large flares are coronal mass ejections, enormous clouds of magnetized plasma launched from the Sun's corona into space. Saturn's rings are one of the most iconic sights in the solar system. When these clouds reach Earth, typically 1 to 3 days after the originating flare, they interact with Earth's magnetosphere, compressing it on the sunward side and inducing electrical currents in the ground below. In extreme cases, these geomagnetic storms can damage or destroy power grid transformers, causing widespread outages. The most powerful geomagnetic storm in recorded history, the Carrington event of 1859, induced currents strong enough to set telegraph machines on fire and produce auroras visible as far south as the Caribbean. The sun gives us light and warmth, but occasionally it reminds us that it is also a star. On clear nights near Earth's poles, the sky sometimes comes alive. Curtains of green ripple across the darkness. Arcs of red and violet shift and fold. Rays of pale white light reach upward from the horizon, moving with a fluid, unhurried grace that makes them appear almost alive. These are auroras, among the most visually striking phenomena in the natural world, and among the most direct, visible expressions of the relationship between the Sun and Earth. Seen through even a small telescope, they are immediately striking. A perfect, luminous disk encircling a giant world, elegant and seemingly eternal. Auroras occur when charged particles from the Sun, electrons and protons carried by the solar wind or ejected in coronal mass ejections, penetrate Earth's magnetosphere near the poles, where the magnetic field lines converge and dip toward the surface. These particles collide with atoms and molecules in the upper atmosphere, exciting them to higher energy states. As those atoms return to their ground states, they release the excess energy as light, green from oxygen at lower altitudes, red from oxygen higher up, blue and purple from nitrogen. The frequency and intensity of auroras is not constant. It follows the Sun's 11-year magnetic cycle. During solar maximum, when sunspot activity is high and the Sun is releasing more frequent and powerful bursts of charged particles, auroras become more common and extend to lower latitudes, visible in strong events from locations well outside the polar regions. During solar minimum, auroral activity quiets. The Sun's internal rhythm, cycling through its magnetic heartbeat once every 11 years, writes itself in light across Earth's polar skies. Each aurora is a message, a visible signature of the Sun's current state, painted in the upper atmosphere by particles that left the Sun days or hours before. A comet approaching the inner solar system is, in some ways, deceptively simple in appearance. A bright core surrounded by a hazy coma of sublimating gas and dust, trailing what appears to be a single luminous tail, stretching away through the darkness. But they are not eternal. But look more carefully, and there are two tails. And both of them are always pointing away from the Sun. This is one of the more counterintuitive facts about comets. A tail, by ordinary analogy, should trail behind a moving object, the way smoke trails behind a chimney or weight trails behind a boat. But a comet's tails do not trail behind it. They are pushed away from the Sun regardless of the comet's direction of travel. When a comet is moving away from the Sun, its tails actually point ahead of it. The reason is solar pressure. The Sun continuously emits both radiation and a stream of charged particles, the solar wind. Both of these exert pressure on the material surrounding a comet's nucleus. Dust particles, released as the nucleus sublimates, are pushed outward by radiation pressure, forming the broader curved dust tail, which traces a gentle arc following the comet's orbital path. The rings are disappearing. Ionized gas in the coma is pushed more directly outward by the solar wind, forming the straight, narrow ion tail, which points almost exactly in the direction away from the Sun. Two tails caused by two different forces, both pointing away from the same source. A comet moves through space trailing light, but that light is not awake. It is a wind shadow, the visible shape of the sun's invisible push. The solar system's moons did not all form the same way. Some coalesced from the same disk of material that surrounded their host planet during formation, building gradually from debris in orbit, accumulating over millions of years into spherical bodies through the same accretionary processes that formed the planets themselves. Most of the regular moons of the gas giants, those with circular prograde orbits close to the equatorial plane, likely formed this way. Others were captured. Small bodies passing too close to a massive planet were slowed by gravitational interactions and drawn into orbit. Many of the irregular moons of Jupiter, Saturn, Uranus, and Neptune, those with eccentric or retrograde orbits, often far from the planet, are thought to be captured asteroids or Kuiper belt objects. Slowly, gradually, and without drama, but disappearing nonetheless. And some were born from violence. Earth's moon is the most studied example. The giant impact hypothesis proposes that early in Earth's history, a body approximately the size of Mars, designated Theia, struck the young Earth in a glancing collision of extraordinary force. The impact vaporized much of both bodies, ejecting an enormous cloud of molten rock and vapor into Earth's orbit. Over thousands of years, that debris cooled and accumulated under its own gravity, eventually forming the Moon. Pluto's largest moon, Charon, so large relative to Pluto that the two are sometimes called a binary system, is also thought to have formed through a similar giant impact event. These collision-born moons carry within their composition the record of the catastrophes that created them. They are not accidents of orbital capture or gradual accretion. They are the lasting consequences of the solar system's most violent moments, shaped into spheres by gravity and set in orbit by the energy of ancient impacts. In 1977, 2 spacecraft left Earth on trajectories that would carry them beyond every planet, beyond the asteroid belt, beyond the Kuiper belt, and eventually out of the solar system entirely. Ice particles and charged material from the rings are drawn inward along Saturn's magnetic field lines, falling into the planet's upper atmosphere in a process scientists call ring rain. Voyager 1 and Voyager 2 were scientific missions first, designed to take advantage of a rare alignment of the outer planets that would not recur for another 176 years, allowing a single spacecraft to visit multiple planets using gravitational assists. The data they returned transformed our understanding of Jupiter, Saturn, Uranus, and Neptune, revealing ring systems, active volcanoes, complex atmospheres, and dozens of previously unknown moons. But attached to the side of each spacecraft was something that had nothing to do with planetary science. A golden record. 12 inches in diameter, made of copper plated with gold, each record contains 115 images, greetings in 55 languages, and approximately 90 minutes of music, ranging from Beethoven to Chuck Berry, from Azerbaijani folk music to a pygmy girl's initiation song. It includes the sounds of surf and wind and thunder, of birds and whales, and a mother's first words to a newborn child. Encoded on its surface is also a map showing the location of our Sun relative to 14 pulsars, a navigational key for any finder capable of reading it. The records were assembled under the direction of Carl Sagan and a small team, working with the understanding that they were creating something intended not for any human audience, but for whatever intelligence might someday find it. In 1,000 years, or 1,000,000, or never. Voyager 1 is now more than 23 billion kilometers from Earth. It is the most distant human-made object in existence. Over time, this steady loss is depleting the rings from within. The golden record it carries has traveled farther from its origin than any physical object our species has ever produced. It drifts through the dark between stars, carrying the sounds of a living world, ocean waves, laughter, music, into a silence so vast and so complete that those sounds may never be heard by anyone. And yet they were sent. That gesture, made in full knowledge of its improbability, says something about the kind of creature that made it. Earth orbits the Sun alone. Or so it appears. In reality, our planet shares its general region of space with a small population of asteroids that follow paths so closely related to Earth's own orbit that they have persisted as near companions for thousands of years. These are co-orbital asteroids. They do not orbit Earth. They are not moons, and they do not remain at a fixed distance from us. But their orbits around the Sun are so similar to Earth's that gravitational interactions keep them in a stable relationship with our planet over long timescales. Data from the Cassini spacecraft, which orbited Saturn for 13 years before its mission ended, suggested something surprising. The rings may be relatively young. Some occupy what are called Lagrange points, specific locations in space where the gravitational influences of the Sun and Earth combine to create regions of relative stability. Objects at the L4 and L5 Lagrange points, located 60 degrees ahead of and behind Earth in its orbit, can remain there for extended periods. These are known as Trojan asteroids. Earth has at least one confirmed Trojan, a small body designated 2010 TK7, discovered in 2010, which oscillates around the L4 point ahead of us in our orbit. Others follow horseshoe orbits, paths that carry them alternately ahead of and behind Earth over cycles lasting centuries, approaching but never quite catching up or being caught, before the geometry reverses and the pattern repeats. These objects are invisible to the naked eye, known only through telescope surveys and orbital calculations. They are not companions in any meaningful physical sense. They pass no closer than millions of kilometers. But they are there. Fellow travelers, sharing our path around the Sun, drifting in quiet gravitational lockstep with a planet that does not know they exist. Neptune is the farthest of the 8 known planets. Perhaps less than 100 million years old, a brief moment by planetary standards. It moves so slowly across the sky, taking 165 years to complete a single orbit, that from one night to the next, from 1 month to the next, its position among the stars barely changes. This slowness, combined with its relative faintness, made it nearly invisible to astronomers who were not specifically looking for it. And the historical record suggests that several of them may have seen it without realizing what they were seeing. The most remarkable case involves Galileo Galilei. In December 1612 and January 1613, Galileo was observing Jupiter and its moons when he recorded the positions of nearby stars. Analysis of those records, conducted centuries later, revealed that one of the points of light Galileo marked as a star was actually Neptune. On at least one occasion, he may even have noted that it had moved slightly between observations, but he attributed the movement to an error or to the motion of a background star and did not pursue it further. Had Galileo recognized what he was seeing, Neptune would have been discovered more than 2 centuries before it actually was. Instead, it waited, moving slowly through the star fields, occasionally observed and misclassified, until the mathematical work of Leverrier and Adams in the 1840s finally drew attention to the exact position where telescopes needed to look. And at current rates of loss, they may be gone entirely within another few 100 million years. A planet present in our observations for centuries, hiding not in darkness but in plain sight, mistaken, overlooked, and patient. Every planetary atmosphere in the solar system is, to some degree, impermanent. The gases that make up an atmosphere are not locked in place. Individual molecules at the upper boundary of an atmosphere, the exosphere, move at speeds determined by their temperature. If a molecule moves fast enough and is light enough, it can reach escape velocity and drift away into space, lost forever from the planet's gravitational grip. This process, called atmospheric escape, affects every planet differently. The rate of escape depends on the planet's gravity, its atmospheric temperature, the mass of the gas molecules involved, and the intensity of solar radiation and solar wind at the planet's distance from the Sun. Light gases, hydrogen and helium, escape most easily. Even Earth, with its relatively strong gravity and protective magnetic field, loses several kilograms of hydrogen to space every second. This loss is more than compensated by various geological and biological sources that replenish the atmosphere over time, so Earth's atmospheric composition remains stable across human timescales. The rings we see when we look at Saturn tonight are not a permanent feature of the solar system. But on smaller, less protected worlds, the losses are more significant. Mars, with its weaker gravity and absent magnetic field, has lost much of the atmosphere it once possessed. The solar wind strikes its upper atmosphere directly, stripping ions away in a process that has been directly measured by the MAVEN spacecraft in orbit around Mars. What remains is a thin, cold remnant of what was once, perhaps, a much thicker and warmer envelope of gas. Every atmosphere is a balance between the processes that generate and retain gas and the slow, continuous leak that drains it away. On most worlds, over long enough timescales, the leak wins. The relationship between planetary rings and moons is not simply one of contrast. Large, round moons on one hand, flat rings of debris on the other. The two are connected, and the connection runs in both directions. Rings can form from moons. When a moon crosses the Roche limit and is torn apart by tidal forces, its debris spreads into a ring. They are a phase, but rings can also form moons. Given the right conditions, ring material can accumulate into larger bodies through the same accretionary processes that built the planets, provided it is far enough from the planet that tidal forces pull apart aggregates rather than allow them to grow. The boundary between these two regimes is the Roche limit itself. Inside it, tidal forces dominate and ring material remains dispersed. Outside it, gravity can overcome tidal disruption, and material can clump together into moonlets. Saturn provides the clearest examples of this process. Pan and Daphnis are two small moons orbiting within gaps in Saturn's ring system. Their shapes, Pan in particular, has a distinctive flying saucer profile, suggest they formed as ring material accumulated around a seed body, with material from the rings gradually piling onto their equators as they orbited within the ring plane. These moonlets are still embedded in the rings today, their gravity carving the gaps in which they orbit, their shapes still being modified by the material around them. They are moons in the process of becoming, caught at an intermediate stage between dispersed ring particles and fully formed satellites. A shimmering, temporary arrangement of ice and light, beautiful precisely because, like so many beautiful things, they will not last forever. In Saturn's rings, planetary formation is still happening. Slowly, quietly, and in miniature. More than 45 years after its launch, Voyager 1 is still functioning. It has crossed the heliopause, entering the interstellar medium, the space between stars, in 2012. It now travels through a region no spacecraft has ever previously explored, measuring the properties of interstellar space directly, the density and temperature of plasma, the intensity of cosmic rays, the strength and direction of magnetic fields originating not from our Sun, but from the broader galaxy. Communication with Voyager 1 presents challenges that grow with each passing year. The spacecraft is currently more than 23 billion kilometers from Earth. A radio signal, traveling at the speed of light, takes more than 22 hours to make the one-way journey. Mission controllers send a command, and then wait nearly 2 days for a response. The spacecraft's power source, a radioisotope thermoelectric generator, converting the heat of radioactive decay into electricity, produces less power each year as its plutonium fuel gradually decays. Mars is often described as a quiet world. To compensate, instruments and systems have been powered down one by one over the decades, conserving electricity for the most scientifically valuable measurements. Engineers at NASA's Jet Propulsion Laboratory continue to communicate with Voyager 1 using the Deep Space Network, a system of large radio antennas located on 3 continents, designed to maintain contact with spacecraft at the farthest reaches of the solar system and beyond. The signal that arrives from Voyager 1 is extraordinarily faint, a whisper from the edge of the known, carrying data from a place no human instrument has ever been before. It is still out there, still moving, still listening, still sending back what it finds. The solar system is in motion. Not just the planets orbiting the sun, or the moons orbiting the planets, or the asteroids tumbling through the belt, but the sun itself and everything it carries with it, moving through the Milky Way galaxy at approximately 220 kilometers per second. The sun follows a broad, roughly circular orbit around the galactic center, a journey so vast that it takes between 225 and 250 million years to complete. Cold, thin-aired, and still. This period is sometimes called a cosmic year or a galactic year. It is one of the largest natural timescales associated with our solar system. In the approximately 4.6 billion years since the solar system formed, the Sun has completed roughly 20 of these galactic orbits. During each orbit, it passes through different regions of the galaxy, moving in and out of the spiral arms, through regions of varying density and stellar activity, occasionally passing near molecular clouds or regions of enhanced cosmic ray flux. These large-scale movements may have consequences over geological time. Passages through dense interstellar regions could alter the shape of the heliosphere, potentially increasing the flux of cosmic rays reaching the inner solar system. Close approaches to other star systems, rare but not impossible over hundreds of millions of years, could perturb the outer Oort cloud, sending showers of comets inward toward the planets. We tend to think of the solar system as fixed in space, with motion confined to the local scale of planets and moons. But at the larger scale, we are passengers on a star that has been orbiting the galaxy since before complex life existed on Earth. The solar system has completed 20 laps, and for much of its year, that description holds. And it is, right now, somewhere in the middle of its 21st. And so our journey comes gently to a close. We have drifted from the scorching surface of Mercury to the frozen edges of the Oort cloud. We have passed through the storms of Jupiter, the rings of Saturn, the dark ocean beneath the ice of Europa. We have followed the path of Voyager into interstellar space, watched diamonds fall through the atmosphere of Neptune, and traced the slow retreat of our own moon across geological time. Each of these things is real. Each of them is happening, right now as you lie still in the dark, somewhere out there in the same solar system you have always inhabited. The storms are turning. The ice is shifting. The golden record is drifting. But Mars has another side. The sun is burning, quietly and steadily, converting itself into light. You don't need to hold any of it. You don't need to remember any particular fact or carry any of it into tomorrow. It was simply here, offered gently, something to let your thoughts rest against as the day finally releases its hold. If these quiet journeys through science help you find your way to sleep, consider leaving a like and subscribing to the channel. It helps others find their way here too. For now, let the solar system continue without you for a few hours. Let your breath slow. Let the darkness settle. The planets will keep their orbits. Dust storms on Mars are unlike anything on Earth. The moons will keep their vigil. The sun will keep its fire. And you can simply rest. Good night. End of script. Sweet dreams. They begin as small, localized gusts, wind picking up the fine iron oxide dust that coats the surface. Under the right conditions, those gusts grow. The dust heats the air around it, creating more wind, which lifts more dust, which heats more air. The feedback loop can escalate until the storm covers an entire hemisphere, sometimes the entire planet. These global storms can last for weeks, sometimes months. The dust is so fine and light that it remains suspended in the atmosphere long after the winds die down, filtering the sunlight into a deep reddish haze and dropping temperatures across the surface. In 2018, one such storm brought an end to the Opportunity rover's mission. The rover had operated for nearly 15 years, but when the dust settled over its solar panels and the sky went dark, it fell silent. Controllers sent one final command. There was no response. Mars is quiet, yes, but it is not a passive world. Beneath that stillness, something restless occasionally stirs. Jupiter's moon, Europa, is, from a distance, a smooth and almost featureless sphere of ice. It reflects sunlight cleanly. It appears cold and still. But beneath that frozen surface, something may be moving. The evidence has been building for decades. Tidal forces from Jupiter's immense gravity flex Europa's interior continuously, squeezing and releasing the moon as it orbits, generating heat deep within. That heat, scientists believe, may be enough to maintain a vast ocean of liquid water beneath the ice. An ocean that may be deeper than any on Earth, sealed beneath a shell perhaps tens of kilometers thick. The surface offers clues. It is crisscrossed with dark lines and ridges, signs of ice that has cracked, shifted and refrozen over time. Spacecraft have detected magnetic signatures consistent with a conducting liquid layer beneath. Chemical traces in the ice hint at a complex active environment below. What makes Europa remarkable is not just the possibility of water. It is the possibility of what water might support. A dark, pressurized ocean warmed from below, potentially rich in the chemical ingredients for biology, existing right here, within our own solar system, orbiting a planet visible to the naked eye. It is one of the most quietly extraordinary places we have ever identified. Return with me to Mars for a moment. In the planet's western hemisphere, rising from the surrounding plains with a gentleness that belies its scale, stands the largest volcano in the solar system, Olympus Mons. It reaches nearly 22 kilometers above the Martian surface. That is almost 3 times the height of Mount Everest. It is so wide, wider than the entire state of New Mexico, that if you stood at its base, the summit would be beyond the horizon. You could walk across it without ever feeling like you were climbing a mountain. Its size is a consequence of Mars's stillness. On Earth, tectonic plates move slowly over volcanic hotspots, creating chains of mountains as the crust shifts. The Hawaiian Islands are one example, a trail of peaks left behind by a moving plate passing over a fixed source of magma. On Mars, the crust does not move. So when a hotspot formed beneath what would become Olympus Mons, the magma erupted in the same place, again and again, over hundreds of millions of years. Layer upon layer, the mountain grew, unchecked, uninterrupted, accumulating into something almost beyond scale. It stands there still, silent, enormous, patient. Saturn's rings stretch more than 280,000 kilometers from one side to the other. That is nearly 3/4 of the distance from Earth to the Moon. And yet, in most places, they are less than 100 meters thick. To put that in proportion, if Saturn's rings were scaled down to the size of a sheet of paper, they would be far thinner than the paper itself, thinner than a human hair relative to their width. It is one of the most extreme aspect ratios of any natural structure in the solar system. The rings are made mostly of water ice, fragments ranging from microscopic grains to boulders the size of houses. This ice gives them their brightness, their almost luminous quality when sunlight strikes them at the right angle. But when that same sunlight passes through the ring plane edge-on, they nearly vanish. A sheet of glass turned sideways. Their flatness is maintained by Saturn's gravity, by the collective dynamics of billions of orbiting particles, and by the subtle gravitational nudging of small shepherd moons that patrol the ring edges, keeping the material from spreading. From a distance, the rings look solid. They look permanent, but they are neither. They are a thin, shifting, breathing structure held together by nothing more than gravity and the quiet mathematics of orbital motion. Of all the planets orbiting our Sun, Earth is the densest. This means that for its size, Earth contains more mass packed into each unit of volume than any other planet, including giants like Jupiter and Saturn, which dwarf us in scale but not in substance. Earth's average density is approximately 5.5 grams per cubic centimeter. Jupiter, despite being more than 1,300 times larger in volume, has an average density less than a quarter of that. Earth's high density comes from its composition: a core of iron and nickel at the center, a thick mantle of dense silicate rock surrounding it, a relatively thin crust on top. The planet is, in essence, a layered metal sphere wrapped in stone. This internal structure matters beyond mere geology. The motion of molten iron in Earth's outer core is what generates our magnetic field, the invisible shield that deflects solar wind and protects the atmosphere. Our planet's density is not just a number. It is the reason we have a magnetosphere, the reason our atmosphere has survived for billions of years, the reason we are here at all. The sun is not silent. You cannot hear it. Space carries no sound, and even if it did, the frequencies involved would be far below the threshold of human hearing. But the sun is nevertheless filled with sound. Pressure waves ripple continuously through its layers, generated by the rising and falling currents of hot plasma that move through its interior like slow, enormous tides. These oscillations cause the entire sun to vibrate. Different regions pulse at different frequencies. The surface rises and falls by small amounts, sometimes just a few kilometers, in patterns that repeat and overlap, like the overtones of a vast and complex instrument. Scientists study these vibrations through a field called helioseismology. By tracking the precise movements of the sun's surface using sensitive instruments, researchers can trace the paths of those internal waves and use them to map what lies beneath: the temperature, the density, the flow of material deep inside a star we cannot otherwise see into. In this way, the sun reveals itself through rhythm, through the slow, inaudible music of its own interior, a song that has been playing for 4.5 billion years, heard not by ears, but by mathematics. Almost every planet in the solar system rotates in the same direction, counterclockwise when viewed from above the sun's north pole. This is the direction inherited from the rotating cloud of gas and dust from which the solar system formed. Most planets kept that original spin as they coalesced. Venus did not. Venus rotates in the opposite direction. On Venus, the sun rises in the west and sets in the east. This retrograde rotation is one of the planet's most enduring mysteries. Some scientists believe it was caused by a massive collision early in the solar system's history, an impact so powerful it reversed the planet's spin entirely. Others suggest that tidal interactions with the sun, acting over billions of years, gradually slowed and then flipped its rotation. Whatever the cause, the result is stranger still when you consider the timing. Venus rotates so slowly that a single day, one full rotation on its axis, takes 243 Earth days. Its year, by contrast, takes only 225. A day on Venus is longer than its year. The sun rises in the west. Time moves differently, and the planet turns in quiet, unhurried defiance of everything around it. Jupiter is the largest planet in the solar system, but its dominance is not only a matter of size, it is also a matter of company. As of now, astronomers have confirmed more than 90 natural satellites orbiting Jupiter, and the count continues to grow as telescopes improve and surveys of the outer solar system become more thorough. It is less a planet with moons than a planet with a system. A miniature solar system of its own, bound together by the immense gravity of the giant at its center. The four largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named for the astronomer Galileo Galilei, who first observed them in 1610. At the time, their discovery was revolutionary. Here were four celestial bodies clearly orbiting something other than Earth, direct evidence that not everything in the cosmos moved around us. Beyond these four giants lies a swarm of smaller irregular satellites. Many orbit in the wrong direction. Some are just a few kilometers across. Some were almost certainly captured from the asteroid belt or the outer solar system, drawn in by Jupiter's gravity over billions of years and never released. Together, they form a scattered orbiting family, held in place by the same force that shapes everything in Jupiter's neighborhood. Gravity, patient and absolute. Mercury is a world of extremes. During the day, its surface reaches temperatures above 400 degrees Celsius. Without an atmosphere to hold that heat overnight, the night side plunges to nearly negative 200 degrees. It is a planet of violent contrasts, scorching and freezing, illuminated and dark, in rapid and relentless alternation. And yet, at its poles, something entirely unexpected has been found. Ice. Mercury's axis has almost no tilt. This means that deep inside certain craters near the poles, the sun's rays never reach. The floors of these craters exist in permanent shadow, cold traps that have maintained temperatures far below freezing for millions, perhaps billions of years. Protected from sunlight by the crater walls above them, these regions act as natural freezers at the edge of the most sun-exposed planet in the solar system. Radar observations from spacecraft, including the Messenger probe, confirmed the presence of bright reflective material in these shadowed regions, consistent with water ice. Scientists believe the water arrived through comet impacts or through ancient volcanic outgassing, deposited long ago and preserved ever since in darkness. In the heart of the hottest planet, locked in shadow, ice endures. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more complex and active than anyone had expected. Among its most striking features was a vast, smooth, heart-shaped plain in the northern hemisphere, a bright expanse of nitrogen ice now known as Sputnik Planitia. It is enormous, roughly the size of Texas, and it is strangely, almost impossibly flat. That flatness is a clue. The weight of such a large basin would, over time, cause the planet to reorient itself, to slowly rotate until the heaviest region aligned with a particular gravitational axis. The fact that Sputnik Planitia sits where it does suggests that something beneath it is adding mass. Something dense. Something liquid. Scientists believe there may be a subsurface ocean beneath Pluto's icy crust, kept from freezing entirely by heat generated through radioactive decay in the planet's rocky interior and insulated from the cold above by thick layers of ice. Pluto sits nearly 6 billion kilometers from the Sun. It spends most of its long orbit in temperatures that approach -230 degrees Celsius. And yet, if this theory is correct, somewhere beneath that frozen heart, liquid water has persisted for billions of years. Even in the coldest reaches of the solar system, warmth finds a way. If you have ever watched a science fiction film set in space, you have almost certainly seen a version of the asteroid belt. A dense, chaotic field of tumbling rocks, barely navigable, requiring constant evasive maneuvers to pass through safely. The reality is almost the opposite. The asteroid belt, which lies between Mars and Jupiter, contains millions of rocky bodies, remnants from the early solar system that never coalesced into a planet, held in a state of perpetual almost by Jupiter's gravitational interference. But these objects are spread across an enormous volume of space. The average distance between asteroids in the belt is hundreds of thousands of kilometers. A spacecraft traveling through the asteroid belt, as many have, would almost certainly never come close enough to any single asteroid to see it. The belt is, in practical terms, mostly empty. Its total mass is less than 5% of the Moon. Its largest resident, the dwarf planet Ceres, accounts for roughly a third of that on its own. The rest is distributed among countless smaller fragments, each one a frozen relic of the solar system's formation, drifting in silence through the space between worlds. Not a wall of rock, not a hazard, just quiet, scattered debris, ancient and unhurried, floating in the dark. Every planet in the solar system is tilted. Earth is tilted about 23.5 degrees. Mars is tilted similarly. Even the gas giants lean slightly as they orbit the Sun. Uranus is tilted 98 degrees. This means that instead of spinning upright like a top, Uranus essentially rolls along its orbital path on its side. Its poles point almost directly toward the Sun at different points in its orbit, rather than its equator. The geometry of its seasons is unlike anything else in the solar system. Each of Uranus's poles experiences approximately 42 years of continuous sunlight, followed by 42 years of complete darkness. During the long polar summer, one hemisphere bakes under uninterrupted sunlight, while the other sits in total night. Then slowly the planet rolls on and the situation reverses. The cause of this extreme tilt is still debated. The leading theory is a catastrophic collision long ago. A body perhaps the size of Earth striking the young Uranus with enough force to knock it sideways. Whether that is what happened, we cannot say for certain. But something, at some point, fundamentally changed the way this planet moves through space. And it has been rolling quietly and steadily ever since. Jupiter's magnetic field is the strongest of any planet in the solar system. It extends millions of kilometers into space, far beyond the orbits of several of its moons, enveloping everything nearby in an invisible but extraordinarily powerful structure. Within that field, charged particles accumulate. Trapped by magnetic forces, these particles, electrons, protons, and heavier ions, are accelerated to enormous energies and confined in dense bands around the planet. These are Jupiter's radiation belts, and they are, by almost any measure, lethal. The radiation within these belts is estimated to be many thousands of times more intense than Earth's own Van Allen belts. An unshielded human being caught within them would receive a fatal dose of radiation within minutes. Even spacecraft must be carefully designed and shielded to survive extended exposure. Jupiter's Galilean moons orbit within or near these belts, and the radiation affects their surfaces, altering chemistry, influencing potential habitability, and complicating any future mission designed to search for life in Europa's ocean. It is a reminder that the outer solar system, for all its quiet beauty when viewed from a safe distance, is not a gentle environment. Jupiter is magnificent, It is also dangerous, and it does not distinguish between the two. The solar system contains 8 planets, hundreds of moons, millions of asteroids, billions of comets, and an uncountable number of smaller bodies scattered across billions of kilometers of space. All of it, combined, accounts for less than 1/5 of 1% of the solar system's total mass. The Sun holds the rest. More than 99.8% of all the mass in the solar system belongs to a single object, the star at its center. Everything else, every planet and moon and drifting fragment of rock and ice, is little more than a rounding error by comparison. This immense mass is what makes the Sun what it is. It is the source of the gravitational pull that keeps every planet in its orbit, every comet on its long elliptical path, every distant body in the Oort cloud loosely tethered to the system. Remove that mass and the solar system dissolves, its members drifting away into the galaxy in all directions. The Sun does not merely illuminate the solar system, it defines it. It holds it together. It is the reason there is a solar system at all. Everything else simply orbits in its presence. The Sun holds everything in place, from the innermost rocky planets to the most distant frozen bodies at the edge of its gravitational reach. And in those cold outer regions, beyond the orbit of Neptune, the solar system turns out to be far more populated than we once believed. For most of human history, we thought we knew how many planets there were. The number changed over time, growing as telescopes improved, shrinking when Pluto was reclassified in 2006. Today, the official count stands at 8, but that reclassification did not reduce the solar system. It revealed something about it. When Pluto was reclassified, it was placed into a new category, dwarf planet. And it was immediately clear that Pluto was not alone in that category. Not even close. Eris, discovered in 2005, is roughly the same size as Pluto and orbits even farther from the Sun. Haumea is a fast-spinning, egg-shaped world coated in crystalline ice. Makemake is a reddish, frozen body orbiting in the cold dark of the Kuiper Belt. And these are only the ones large enough and bright enough to have been found so far. Scientists estimate that there may be hundreds, possibly thousands, of dwarf planets waiting to be discovered in the outer solar system. Objects large enough to have been pulled by their own gravity into a roughly spherical shape, but not large enough to have cleared their orbital neighborhoods. The solar system is not smaller than we thought. It is larger, far more complex, and full of worlds we are only beginning to find. Titan is Saturn's largest moon, and it is unlike anywhere else in the solar system. It has a thick atmosphere, thicker in terms of surface pressure than Earth's own. It has weather. It has clouds, rain, rivers, lakes, and seas. From a distance, or viewed through the right instruments, it resembles a planetary body that could almost be familiar. But nothing on Titan is made of water. The lakes and seas that cover Titan's polar regions are filled with liquid methane and ethane, hydrocarbons that exist as gases on Earth but flow freely as liquids in Titan's extreme cold, where temperatures hover around negative 179 degrees Celsius. Methane rain falls from hydrocarbon clouds and runs in rivers across a landscape sculpted not by water erosion, but by entirely different chemistry. And yet beneath all of this alien strangeness, scientists believe Titan may also harbor a more familiar kind of ocean. Deep beneath its icy crust, there may be liquid water, a subsurface sea, warmed by internal heat, sealed away from the methane world above. Titan is a world of layered mysteries. On its surface, chemistry we have never encountered elsewhere. Below, perhaps, something that feels almost like home. Mars has 2 moons, but they do not look like moons. Phobos and Deimos are small, irregular, and heavily cratered. shaped less like the spherical satellites we associate with planets and more like oversized asteroids that wandered too close and never left. Which, according to the leading theory, may be exactly what happened. Many scientists believe Phobos and Deimos were once part of the asteroid belt, rocky bodies that drifted into Mars's gravitational influence long ago and were captured into orbit. Their low densities, their irregular shapes, and the composition of their surfaces all support this idea, bearing more resemblance to outer belt asteroids than to material that would have formed around Mars directly. Their futures are as different as their origins might suggest. Phobos orbits so close to Mars and is being slowed so gradually by tidal forces that it is spiraling inward. Within perhaps 50 million years, it will come close enough to be torn apart by Mars's gravity, either scattering as a ring of debris or breaking into fragments that fall across the Martian surface. Deimos, meanwhile, is drifting in the other direction, slowly, quietly, moving away. 2 moons, opposite trajectories, and a planet between them, watching in silence. Jupiter receives sunlight, but it gives back more than it takes. Unlike the rocky planets, which absorb solar energy and radiate it back into space in roughly equal measure, Jupiter emits significantly more heat than it receives from the Sun. The excess energy comes not from nuclear fusion. Jupiter is not massive enough to be a star, but from a process almost as ancient. When Jupiter formed, roughly 4.5 billion years ago, an enormous amount of gas and dust collapsed inward under its own gravity. That collapse released gravitational energy as heat, and Jupiter has been slowly radiating that primordial warmth ever since. The planet continues to contract very slightly, imperceptibly slowly but measurably, and that ongoing compression generates additional heat. This internal energy drives Jupiter's turbulent weather systems, its swirling cloud bands, and its massive storm systems far more than sunlight alone ever could. If Jupiter had been perhaps 80 times more massive, the pressures in its core might have been sufficient to ignite nuclear fusion, and it would have become a star. Instead, it sits at the threshold, a giant world glowing faintly from within, radiating ancient warmth into the cold of the outer solar system. Almost a star. Not quite, but luminous in its own quiet way. Most planets were discovered the same way, by looking up. Ancient astronomers identified Mercury, Venus, Mars, Jupiter, and Saturn with the naked eye over thousands of years of careful observation. Uranus was discovered in 1781 when William Herschel pointed a telescope at a point of light that moved differently from the stars around it. Neptune was found by an entirely different method. After Uranus was identified and its orbit carefully mapped, astronomers noticed something troubling. The planet was not moving quite as it should. Its path deviated slightly from the predictions of Newtonian gravity, small but consistent irregularities that suggested something unseen was pulling at it. In the 1840s, 2 mathematicians working independently, Urbain Le Verrier in France and John Couch Adams in England, used those orbital deviations to calculate where a hidden planet must be. They worked not with telescopes, but with equations, tracing the invisible influence of an undiscovered world through pure mathematics. When astronomers pointed their telescopes to the predicted position in 1846, Neptune was there, exactly where the mathematics said it would be. It was the first planet found on paper before it was seen through glass. A world brought into existence for human knowledge, not by observation, but by reason. A quiet triumph of the human mind reaching into the dark and finding something real. At Saturn's North Pole, a storm has been spinning for decades, possibly centuries. What makes it extraordinary is not its size, though it is vast, spanning more than 30,000 kilometers across. wider than 2.5 Earths placed side by side. What makes it extraordinary is its shape. It is a hexagon, a nearly perfect six-sided geometric form traced in the clouds of a giant planet's atmosphere. Each side of the hexagon is longer than the diameter of Earth. The entire structure rotates slowly and steadily, maintaining its shape with a precision that seems almost architectural. Scientists believe the hexagon forms through the dynamics of Saturn's rotating atmosphere, specifically through the interaction of a fast-moving jet stream with slower-moving air around it. Under certain conditions, rotating fluids can spontaneously organize into polygonal shapes. Laboratory experiments using spinning tanks of water have reproduced similar patterns. And yet, knowing the mechanism does not fully diminish the strangeness of it. A six-sided storm, persistent across human timescales, turning quietly at the pole of a ringed world 400 million miles from Earth. Geometry written in clouds. A pattern so regular it seems deliberate, emerging from nothing but physics and time. The Sun has a surface, and above that surface it has an atmosphere. The surface, called the photosphere, burns at approximately 5,500 degrees Celsius. Hot enough to vaporize any known material. Hot enough to feel across 93 million miles of space as the warmth on your skin on a summer afternoon. But the Sun's outer atmosphere, the corona, is hotter. Far hotter. The corona extends millions of kilometers above the photosphere, thinning gradually into the solar wind. And throughout that vast, diffuse outer layer, temperatures reach 1 million degrees Celsius or more, nearly 200 times hotter than the surface below. This should not be possible. Heat flows from hot to cold. Energy should diminish as it moves away from the source, not increase. And yet the corona blazes at temperatures the surface cannot explain. The precise mechanism remains one of solar physics' most enduring mysteries. One leading theory involves Alfvén waves, magnetic disturbances that carry energy upward from the Sun's interior and deposit it in the corona. Another suggests that countless tiny magnetic reconnection events, called nanoflares, collectively heat the outer atmosphere from below. Whatever the cause, the Sun's outermost layer burns in defiance of intuition, a vast invisible fire surrounding a star hotter than the star itself. The Sun's corona burns with mysterious heat at the solar system's center. As we drift in the opposite direction, outward, past Neptune into the cold, we enter a region that preserves something the inner solar system long ago lost beyond Neptune. The solar system does not simply end. It opens into something wider and older, a vast ring of frozen bodies stretching billions of kilometers from the Sun, remnants of the material that built the outer planets and was never incorporated into them. This is the Kuiper Belt, and it is, in a sense, a fossil record of the solar system's earliest moments. The Kuiper Belt is structurally similar to the asteroid belt, a broad, flat distribution of objects orbiting in roughly the same plane as the planets. But it is far larger, far colder, and composed of different material. Where the asteroid belt contains mostly rock and metal, the Kuiper Belt holds ice, frozen water, methane, and ammonia, preserved at temperatures approaching absolute zero. Among its residents are some of the solar system's most intriguing worlds: Pluto, Eris, Haumea, Makemake. Each one a frozen sphere, each carrying chemical information from the time before the planets fully formed. Each one a small, cold window into the solar system's origin. Scientists study Kuiper Belt objects not just for what they are, but for what they remember. In their ice and their chemistry, they carry a record of conditions that existed 4.5 billion years ago, a time before Earth had oceans, before life existed, before any of this was as it is now. cold, dark, and patient. The Kuiper Belt waits at the edge of what we know. No spacecraft has ever reached it. No telescope has ever directly imaged it. And yet, scientists believe it exists. A vast spherical shell of frozen bodies encircling the entire solar system at an almost incomprehensible distance. This is the Oort cloud. While the Kuiper Belt is a flat disk lying roughly in the plane of the planets, the Oort cloud is thought to be a sphere, surrounding the solar system in all directions, extending perhaps a quarter to a full light year from the Sun. At its outer edge, the Sun's gravity barely holds on. Objects there are so loosely bound that a passing star, a nearby supernova, or even the gentle gravitational tides of the Milky Way itself can dislodge them, sending them falling inward on long, slow trajectories toward the inner solar system. When they arrive, we see them as long-period comets, objects appearing from seemingly nowhere, tracing enormous elongated paths around the Sun before disappearing again into the dark. Some of these comets take thousands of years to complete a single orbit. Some may never return. They are messengers from the solar system's outermost reaches. Ancient ice, preserved for billions of years in near absolute darkness, briefly lit by sunlight before retreating once more. If the Oort cloud exists as theorized, it marks the true gravitational frontier of the Sun's domain, a cold, silent halo of frozen wanderers drifting at the very edge of belonging. Io should not be as it is. By all expectations, a moon of its size, slightly larger than our own moon, orbiting a planet rather than a star, should long ago have cooled and stilled. Its interior should be solid. Its surface should be ancient, cratered, and quiet. Instead, Io is the most volcanically active body in the solar system. Its surface is in a state of near constant eruption. Hundreds of volcanoes dot its landscape, some of them enormous, venting molten sulfur and silicate rock across a terrain that is perpetually being reshaped. Volcanic plumes rise hundreds of kilometers into space. The surface is so young, so continuously renewed by fresh lava, that impact craters, common on almost every other solid body in the solar system, are almost entirely absent. They are buried before they can accumulate. The energy driving all of this comes not from radioactive decay or residual formation heat, but from gravity. Io orbits Jupiter in a precise resonance with two other large moons, Europa and Ganymede. This arrangement ensures that Io is continuously and rhythmically squeezed by competing gravitational forces, Jupiter pulling one way, the other moons pulling another. The friction of that constant flexing heats Io's interior to temperatures sufficient to keep vast regions of its subsurface molten. It is a moon being perpetually kneaded by gravity, and in that kneading it burns. Of all the large moons in the solar system, Triton is the only one that orbits its planet in the wrong direction. Every major moon in the solar system orbits in the same direction as its planet rotates, a consequence of having formed from the same rotating disk of material as the planet itself. Triton does not. It orbits Neptune in the opposite direction, moving backward relative to Neptune's spin in what is called a retrograde orbit. This backward motion is the clearest possible evidence that Triton did not form alongside Neptune. It was captured, a Kuiper Belt object that wandered too close to Neptune's gravitational influence and was drawn into orbit, likely billions of years ago. The disruption caused by that capture may have been catastrophic, potentially destroying whatever moons Neptune originally had and scattering them into new or unstable configurations. Despite its violent origins, Triton today is a world of eerie, cold beauty. Its surface is covered in frozen nitrogen, with a thin atmosphere that shifts and expands as Triton moves closer to the Sun in its orbit. Near its south pole, Geysers of nitrogen gas erupt from beneath the surface, driven by solar heating of the ice below, plumes rising several kilometers into the thin air before being swept downwind. A captured wanderer from the outer dark, moving in reverse, still somehow erupting. The moon is so familiar that it is easy to take for granted. It is simply there, rising and setting, marking the months, lighting the night in its slow phases. But when you consider it in the context of the solar system as a whole, the moon is genuinely unusual. No other rocky planet has a satellite so large relative to itself. Mercury and Venus have no moons at all. Mars has two tiny irregular bodies that are almost certainly captured asteroids. But Earth has a moon with a diameter roughly 1/4 of Earth's own, a ratio more typical of binary systems than of a planet and its satellite. The most widely accepted explanation is the giant impact hypothesis. Early in Earth's history, perhaps 50 million years after the solar system formed, a body roughly the size of Mars, sometimes called Theia, collided with the young Earth at an oblique angle. The impact was not a direct strike, but a glancing blow, enormous enough to vaporize much of both bodies and eject a vast cloud of debris into orbit. Over thousands of years, that debris gradually coalesced into the moon. The consequences of that collision have shaped Earth ever since. The moon stabilizes our planet's axial tilt, preventing the wild swings in obliquity that might otherwise disrupt our climate over millions of years. It drives our tides. It has slowed Earth's rotation over geological time. A moment of ancient catastrophe. A lifetime of quiet influence. For centuries, the dominant model of planetary motion assumed that orbits were circular. The circle was considered geometrically perfect, and perfection, it was assumed, must be what governed the heavens. It was not. In the early 1600s, the German astronomer Johannes Kepler spent years analyzing precise observations of planetary positions, particularly those of Mars, compiled by the Danish astronomer Tycho Brahe. No matter how carefully he tried to fit Mars's motion to a circular orbit, the numbers refused to cooperate. Eventually, reluctantly, he accepted what the data was telling him. Planetary orbits are ellipses, slightly flattened circles, with the Sun positioned not at the center, but at one of two focal points. This means that every planet has a point in its orbit where it is closest to the Sun, called perihelion, and a point where it is farthest, called aphelion. The planet moves faster near perihelion and slower near aphelion, in a continuous, graceful acceleration and deceleration. For most planets, the ellipse is only slightly stretched, close enough to circular that the difference is hard to notice. But for Mercury and Pluto, the ellipses are more pronounced, producing significant variation in their distance from the Sun across a single orbit. The orbits are not perfect. They never were. But there is a different kind of perfection in the ellipse, in the way it emerges inevitably from the mathematics of gravity, elegant and exact. The Sun has been burning for approximately 4.5 billion years. It will burn for approximately 5 billion more. But it will not burn forever. As the Sun exhausts the hydrogen fuel in its core, the nuclear reactions that have sustained it will begin to change. The core will contract under gravity, heating further, while the outer layers expand dramatically, swelling outward into space as the Sun becomes what is known as a red giant. In this phase, the Sun may expand far enough to engulf Mercury, Venus, and possibly Earth itself. The inner solar system, as it exists today, will cease to exist. After the red giant phase, the Sun will shed its outer layers entirely, releasing them into space as an expanding shell of glowing gas called a planetary nebula, briefly illuminating the surrounding region in colors of blue, green, and red before dispersing into the interstellar medium. What remains will be the core, a dense, Earth-sized remnant composed mostly of carbon and oxygen, no longer capable of fusion, no longer producing energy. This is a white dwarf. It will cool slowly, over trillions of years, fading from white to yellow to orange to red, and eventually to something barely distinguishable from the surrounding darkness. The sun will not explode. It will not collapse into a black hole. It will simply gradually go quiet. The sun's future lies billions of years away. A transformation so slow and distant, it barely registers against the rhythms of everyday life. More immediate and perhaps more relatable are the seasonal cycles that govern the worlds closer to home. And one of those worlds, it turns out, experiences something remarkably familiar. Mars is cold. Its atmosphere is thin, less than 1% the pressure of Earth's at sea level. Its surface is dry and largely inhospitable. In almost every measurable way, it is a harder, harsher world than our own. And yet Mars has seasons. The reason is the same as it is on Earth, axial tilt. Mars leans at approximately 25 degrees relative to its orbital plane, nearly identical to Earth's tilt of 23.5 degrees. As Mars orbits the Sun, this tilt causes sunlight to strike each hemisphere more directly at different points in the year, producing the same fundamental cycle of spring, summer, autumn, and winter that shapes life on our own planet. The differences lie in the details. Mars takes nearly twice as long as Earth to complete its orbit, so each Martian season lasts roughly twice as long as its Earth equivalent. The thin atmosphere means temperature swings are more extreme. The polar ice caps, made of both water ice and frozen carbon dioxide, expand and contract with the seasons, and changes in atmospheric pressure follow as carbon dioxide freezes and sublimates across the year. The seasons of Mars are familiar in structure, alien in scale. A slow, cold echo of our own world's rhythm, playing out on a planet that took a different path. Not all moons are small. Ganymede, the largest of Jupiter's Galilean moons, is the biggest natural satellite in the entire solar system. With a diameter of just over 5,200 kilometers, it is larger than the planet Mercury, though its mass is lower as it contains a significant proportion of ice alongside its rock. What makes Ganymede remarkable is not just its size, but its complexity. Beneath its icy, grooved surface lies a differentiated interior, a dense iron core, a rocky mantle, and an outer shell of ice. And between layers of that ice, scientists believe there may be a vast subsurface ocean of liquid water, possibly containing more water than all of Earth's oceans combined. But Ganymede holds one distinction that sets it entirely apart from every other moon in the solar system. It has its own magnetic field. No other moon does. Ganymede generates a magnetic dipole through processes in its metallic core, creating a miniature magnetosphere nested within Jupiter's far larger one. This interaction produces auroras, faint, shimmering rings of light near Ganymede's poles, detectable by spacecraft and telescopes. A moon larger than a planet. A hidden ocean. A magnetic field all its own. Ganymede orbits in Jupiter's shadow, largely overlooked in conversations about the solar system's most dramatic worlds. But it is, quietly, one of the most extraordinary objects we know of. Pluto's orbit is unusual in almost every way. It is highly elliptical, far more stretched than the nearly circular paths of the 8 classical planets. It is also inclined, tilted about 17 degrees, relative to the plane in which most of the other planets orbit. And it crosses, at least on paper, the orbit of Neptune, coming closer to the Sun than Neptune during certain parts of its 248-year journey. This last fact sounds alarming. 2 large bodies, sharing overlapping orbital paths, moving through the same region of space. Surely a collision is inevitable. But it is not. And the reason is one of the most elegant examples of gravitational choreography in the solar system. Pluto and Neptune are locked in what is called an orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This precise ratio means that their positions relative to each other repeat in a perfectly predictable pattern. And crucially, the pattern ensures that whenever Pluto crosses Neptune's orbital distance, Neptune itself is always far away on the other side of the Sun. They never come close. They never will. 2 worlds sharing overlapping paths, held apart not by distance, but by the invisible mathematics of gravitational timing. A dance choreographed by physics itself, running without interruption for billions of years. Roughly every 11 years, the Sun undergoes a transformation that is invisible to the naked eye, but felt across the entire solar system. Its magnetic field reverses. The Sun's north and south magnetic poles switch places, a process driven by the differential rotation of the Sun's plasma. Because the Sun is not a solid body, its equator rotates faster than its poles. Over time, this difference in rotation rates twists and winds the magnetic field lines that thread through the solar interior, building tension until the field becomes unstable and reorganizes itself into the opposite configuration. During the peak of this cycle, called solar maximum, the Sun's surface becomes more active. Sunspots multiply. Solar flares erupt more frequently. Coronal mass ejections send vast clouds of charged particles streaming outward through the solar system. Then gradually, activity subsides. Sunspots become fewer. The solar wind quiets. The Sun enters solar minimum, a period of relative calm before the next cycle begins building toward activity once more. This 11-year rhythm pulses outward through the heliosphere, affecting the intensity of cosmic rays reaching the inner solar system, influencing the frequency and brightness of auroras on Earth, and subtly altering conditions across every planet and moon that lies within the Sun's magnetic reach. The Sun is not a constant star. It breathes. It cycles. It changes. And everything in the solar system changes with it. Every few years, news circulates of an unusual planetary alignment. Several planets gathering in the same region of sky, or arranging themselves in a line extending outward from the Sun. These events are visually striking and mathematically interesting. They are often accompanied by predictions of earthquakes, floods, or other catastrophes. None of those predictions have ever come true. And the reason is simple. The gravitational influence of other planets on Earth is extraordinarily small. Jupiter, the most massive planet in the solar system, exerts a gravitational pull on Earth that is thousands of times weaker than the Moon's. Saturn, Uranus, and Neptune are both less massive and more distant. Their gravitational effects on our planet are smaller still. Even during the most precise planetary alignment imaginable, the combined gravitational effect of all other planets on Earth is negligible compared to the forces already acting on our world every day. The Moon alone, small and nearby, exerts more tidal influence on Earth's crust than all other planets combined. Planetary alignments do not trigger geological events. They do not alter weather patterns. They do not disturb the internal dynamics of our planet in any measurable way. They are beautiful. They are worth watching. On a clear night, seeing several planets arrayed across the sky in a single sweeping line is a genuine reminder of the geometry underlying our solar system. But they are gravitationally harmless. A silent dance of distant worlds, elegant and entirely without consequence. In 1977, humanity launched 2 spacecraft on trajectories that would carry them beyond the planets, beyond the asteroid belt, beyond the Kuiper belt, and eventually out of the solar system entirely. Voyager 1 and Voyager 2 have been traveling ever since. They flew past Jupiter and Saturn, gathering data and images that transformed our understanding of the outer planets. Voyager 2 continued to Uranus and Neptune, the only spacecraft ever to have visited either world up close. Then both probes continued outward, carried by their momentum into the outer reaches of the heliosphere. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in 2012. Voyager 2 followed in 2018. Both are now traveling through interstellar space, the region between stars where the sun's influence fades and the broader galaxy begins. They travel at speeds exceeding 60,000 kilometers per hour, and they have been doing so for nearly 50 years. The distances involved are almost impossible to hold in the mind. Light itself, traveling at 300,000 kilometers per second, takes more than 20 hours to cover the distance between Earth and Voyager 1. A radio signal sent from Earth takes just as long to arrive, and another 20 hours to receive a reply. We built something small enough to hold in a room, and it is now drifting through the space between stars, still sending signals home. Surrounding Earth, generated deep within its interior, is a magnetic field that extends tens of thousands of kilometers into space in all directions. You cannot see it. You cannot feel it. But without it, the world as we know it would not exist. The field is produced by the movement of molten iron in Earth's outer core, a slow, continuous churning driven by the heat flowing outward from the planet's center. This motion of electrically conducting fluid generates electric currents, which in turn produce a magnetic field that wraps around the entire planet in a structure called the magnetosphere. The magnetosphere deflects the solar wind, the constant stream of charged particles flowing outward from the sun. Without this deflection, those particles would strike the upper atmosphere directly, gradually stripping it away over millions of years, much as the solar wind has eroded the atmosphere of Mars. Where the solar wind particles are funneled by the magnetic field toward the poles, they interact with gases in the upper atmosphere and produce auroras, shimmering curtains of green, red, and violet light that ripple across polar skies. These displays are perhaps the most visible reminder of the invisible work the magnetic field performs every moment of every day. Earth's magnetosphere is not a fixed, static structure. It flexes and changes in response to solar activity, compressed on the sun-facing side and stretched into a long tail on the opposite side. It breathes with the solar wind, and in its breathing, it keeps us safe. Earth's magnetic field holds the atmosphere in place and keeps the surface habitable across geological time. But Earth's relationship with the Moon, that other great shaping force in our sky, is also changing. Slowly, quietly, and in only one direction. Every year, the Moon moves approximately 3.8 centimeters farther from Earth. It is not a dramatic departure. At that rate, the Moon recedes by roughly the width of a finger each year, a change so gradual it is entirely imperceptible from one human lifetime to the next. And yet, accumulated across geological time, the effect is profound. The mechanism is tidal friction. The Moon's gravity pulls on Earth's oceans, creating the familiar bulges we experience as tides. But Earth rotates faster than the Moon orbits, which means those tidal bulges are always slightly ahead of the Moon's position. The Moon's gravity pulls back on those bulges, and in doing so, transfers a small amount of Earth's rotational energy to the Moon. The Moon gains energy and moves to a slightly higher orbit. Earth's rotation slows almost imperceptibly in response. Billions of years ago, the Moon was significantly closer. The tides it drove were far more powerful. Days on Earth were shorter, perhaps only 6 hours long in the planet's earliest history. The sky would have been dominated by a Moon appearing much larger than it does today. As the Moon continues its slow retreat, total solar eclipses will eventually become impossible. The moon will appear too small in the sky to completely cover the sun's disk. The geometry that makes those moments of totality so rare and so extraordinary will one day no longer exist. We are living, it turns out, in a particularly fortunate window of time. The Kuiper Belt is a cold and shadowed place. Sunlight arrives there diminished, weakened by distance to a fraction of its intensity at Earth's orbit. Most objects in this remote region are dark, reflecting very little of the faint light that reaches them. But some are not dark at all. Haumea is one of the more unusual residents of the Kuiper Belt, a fast-spinning, elongated world shaped roughly like a flattened egg, rotating so rapidly that it completes a full day in less than 4 hours. Its surface is coated in crystalline water ice, giving it a brightness that stands out against the surrounding darkness. Scientists believe Haumea's surface may have been renewed relatively recently, possibly through cryovolcanic activity or through a collision that exposed fresh ice from beneath. Eris, discovered in 2005 and roughly comparable in size to Pluto, is even more reflective. Its surface reflects nearly all the sunlight that strikes it, a level of reflectivity comparable to freshly fallen snow. This extreme brightness may be the result of a thin layer of frozen methane that condenses onto the surface as Eris moves away from the sun and its thin atmosphere freezes back down. In the cold outer dark, where the sun is little more than a bright star, these distant worlds catch what light there is and send it back with unusual generosity. Cold mirrors, drifting in silence, gleaming faintly at the edge of what we know. Saturn's moon Enceladus is small, roughly 500 kilometers across, small enough to fit comfortably within the borders of a single country. From a distance, it appears as a smooth, bright sphere, one of the most reflective bodies in the solar system. But at its south pole, something extraordinary is happening. From a series of long parallel fractures in the ice, informally called tiger stripes, enormous plumes of water vapor and ice crystals erupt continuously into space. These geysers rise hundreds of kilometers above the surface before dispersing into Saturn's orbit, where they contribute material to the planet's faint E-ring, creating a direct physical connection between moon and planet. The energy driving these eruptions comes from tidal heating. Saturn's gravity flexes Enceladus as it orbits, generating internal warmth sufficient to maintain a liquid ocean beneath the icy crust. That ocean is in contact with a rocky seafloor, and the interaction between warm water and rock produces hydrothermal activity similar to what occurs at the bottom of Earth's own oceans. The plumes carry more than water. Analysis by the Cassini spacecraft detected organic compounds, molecular hydrogen, silica particles, and salts in the ejected material. Chemical signatures consistent with an active hydrothermal system. Some of the compounds identified are associated on Earth with the processes that support life. Enceladus is small. It is cold on the outside. But beneath its ice, a warm, chemically active ocean has been quietly present for a very long time. Not all asteroids are solid rock. Many of the small bodies orbiting in the asteroid belt and elsewhere in the solar system are not monolithic chunks of stone at all. They are rubble piles, loose collections of gravel, dust, and fragments of various sizes held together by nothing stronger than their own gentle mutual gravity. These structures form when a larger asteroid is shattered by a collision, and the debris from that collision gradually drifts back together over time, drawn by the combined gravitational attraction of all its pieces. The result is an object that looks from a distance like a solid asteroid, but is in reality a loosely packed aggregate with large internal voids and no structural strength. Rubble pile asteroids behave strangely under pressure. They can spin rapidly without flying apart because loose material redistributes itself. They compress rather than fracture when struck. They are, in a sense, self-healing. Damage redistributes rather than propagates. Missions to two such asteroids, Hayabusa 2's visit to Ryugu and OSIRIS-REx's visit to Bennu, confirmed their porous, loosely structured nature in remarkable detail. When OSIRIS-REx pressed its sample collection device against Bennu's surface, the spacecraft sank several centimeters into the asteroid before the thrusters fired to pull it back. Ancient, fragile, and barely holding together. These rubble worlds are among the solar system's most delicate survivors. Mercury is the smallest planet in the solar system, smaller than 2 of Jupiter's moons. And yet, inside that small body, something disproportionate lurks. Mercury's iron core extends approximately 80% of the way to the surface. By comparison, Earth's core makes up roughly 55% of our planet's radius. Mercury's core, relative to its total size, is the largest of any planet in the solar system. A dense, metallic heart occupying the vast majority of a world that is itself already remarkably small. The reason for this oversized core is uncertain. One leading theory suggests that Mercury once had a more typical structure, a larger rocky mantle surrounding a proportionally normal iron core, but that a massive collision early in the solar system's history stripped away much of that outer rock, leaving the dense core disproportionately exposed. Another theory proposes that close proximity to the young sun during formation may have selectively evaporated lighter materials, leaving heavier elements behind. Whatever the cause, the result is a planet of unusual density and unusual behavior. Mercury has a weak but detectable magnetic field, surprising for a planet so small and suggestive of at least a partially molten core still in motion. It is a compact, metal-heavy world shaped by forces that acted in the solar system's most chaotic early period. A small planet carrying an oversized past. Among the rocky planets of the inner solar system, 2 have no moons. Mercury's lack of satellites is perhaps understandable. It orbits so close to the Sun that capturing and retaining a moon in a stable orbit is extremely difficult. The Sun's gravity would quickly destabilize most potential satellites. But Venus is different. Venus is roughly the same size as Earth. It orbits at a distance from the Sun where stable satellite orbits should be possible. And yet it has no moon, not a captured asteroid, not a remnant of an ancient collision, not even a small irregular satellite. Why Venus is moonless is a question without a definitive answer. One theory suggests that Venus may once have had a moon, formed from a giant impact similar to the one that created Earth's moon, but that this moon subsequently fell back into Venus due to the planet's unusual retrograde rotation. Another possibility is that tidal interactions with the Sun over billions of years destabilized any satellite that Venus might have acquired. Some researchers have suggested that Venus may have experienced multiple large impacts throughout its history, and that the dynamics of those collisions prevented any stable moon from forming or persisting. Whatever the cause, Venus moves through space alone, brilliant, cloud-wrapped, and companionless. The brightest object in Earth's night sky after the moon, and yet a world with no moon of its own to cast light across its long, slow nights. Some observations require distance. The Hubble Space Telescope orbits Earth at an altitude of approximately 540 kilometers, close enough that, on a clear night, it is sometimes visible to the naked eye as a moving point of light crossing the sky. From that modest perch, it has looked outward across billions of light years, capturing images of galaxies in their infancy, stars in the process of forming, and the deep structure of the universe itself. But it has also looked closer to home. Hubble has spent decades observing the planets of our own solar system, tracking the evolution of Jupiter's storm systems, monitoring seasonal changes on Mars, watching auroras flicker at the poles of Saturn and Uranus, and recording the shifting cloud patterns of Neptune's atmosphere. These are not one-time snapshots. They are part of a long, continuous record of planetary observation stretching back more than 30 years. This long baseline is something no flyby mission can provide. Spacecraft like Voyager and Cassini passed their target planets once, gathering extraordinary data in brief, irreplaceable encounters. Hubble watches the same worlds year after year, building a picture of change over time. Storms that grow and shrink, seasons that advance and retreat, impacts that leave temporary scars and then fade. From low Earth orbit, just above the atmosphere that distorts ground-based telescopes, Hubble has become one of the solar system's most patient and attentive observers. Not traveling anywhere, simply watching. Some things in the solar system refuse to end. In Jupiter's southern hemisphere, a storm has been raging for at least 350 years. The Great Red Spot is the largest and longest-lived storm in the solar system, an anticyclonic system rotating counterclockwise, with wind speeds along its outer edges exceeding 400 kilometers per hour. At its largest, historical observations suggest it may have been wide enough to contain 3 Earths side by side. Today, after a period of gradual shrinkage that has been tracked across decades of observation, it remains large enough to swallow Earth once. The storm's reddish color is not fully understood. The leading explanation involves complex chemical reactions occurring at high altitudes in Jupiter's atmosphere, sunlight interacting with compounds dredged upward from deeper layers, producing the distinctive hues that make the spot immediately recognizable. What keeps it alive is Jupiter itself. On Earth, storms dissipate when they make landfall, when they lose their energy source, or when they are disrupted by terrain. Jupiter has no land, no continents to interrupt the flow, no surface friction to bleed away the storm's energy. The atmosphere simply continues, layer beneath layer, and the Great Red Spot spins on within it, sustained by the same dynamics that created it, in a planet that offers nothing to slow it down. 3.5 centuries of continuous rotation, and no sign yet that it intends to stop. Not everything cold is still. Neptune is the most distant of the 8 known planets. It receives less than 1,000th of the sunlight that reaches Earth. Its cloud-top temperatures hover around -210 degrees Celsius. By almost any measure, it is one of the coldest environments in the solar system. And yet Neptune is not a passive frozen world. It radiates approximately 2.6 times more energy than it receives from the Sun. This excess heat, generated somewhere within the planet's interior and flowing outward through its layers, drives Neptune's atmosphere with a vigor that sunlight alone could never provide. It powers the fastest winds in the solar system. It fuels storm systems that dwarf anything on Earth. It keeps a world that should, by the logic of its distance, be nearly inert in a state of continuous atmospheric turbulence. The exact source of Neptune's internal heat remains uncertain. Possibilities include residual warmth from the planet's formation, slow gravitational contraction, releasing energy as the planet compresses slightly over time, or radioactive decay within its rocky core. Whatever the source, the result is a planet that defies its circumstances. Cold on the outside, energetic within. Far from the Sun, yet driven by an internal engine that the Sun had no part in creating. Neptune is a reminder that in the solar system, appearances are frequently misleading. Distance from a star does not determine a world's energy. Some warmth comes from within. One world holds something no other has managed to keep. Water exists elsewhere in the solar system. It is locked in the ice caps of Mars. It hides beneath the crusts of Europa, Enceladus, and Ganymede. It drifts as vapor in the thin atmospheres of several moons. It coats the surfaces of Kuiper Belt objects in frozen sheets. Water, in one form or another, is not rare. But there is only one place in the solar system where water exists simultaneously and continuously in all three states, solid, liquid, and gas, cycling freely between them across the surface of a planet. That place is Earth. Ice sheets and glaciers store water in solid form at the poles and at high altitudes. Oceans, lakes, and rivers hold it in liquid form across most of the surface. Water vapor fills the atmosphere, forming clouds, driving weather, and returning to the surface as rain and snow. These three forms interact continuously, evaporating, condensing, freezing, melting, in a planetary water cycle that has been running, with variations, for billions of years. This balance is not accidental. It depends on Earth's precise distance from the Sun, the pressure maintained by its atmosphere, and the relatively stable temperatures produced by its climate system and magnetic protection. Move Earth slightly closer to the Sun, and the oceans evaporate. Move it slightly farther, and they freeze. We occupy a narrow window, and within that window, water moves. Every domain has an edge. The Sun produces a constant stream of charged particles, electrons, protons, and heavier ions, that flows outward in all directions at speeds of hundreds of kilometers per second. This is the solar wind, and it does not stop at the outer planets, or at the Kuiper Belt, or even at the orbit of Pluto. It continues outward, thinning gradually until it encounters something pushing back. That something is the interstellar medium, the thin gas and dust that fills the space between stars. Where the solar wind's pressure finally equals the pressure of the interstellar medium, the two flows meet in a turbulent boundary region. Beyond that boundary, the solar wind can go no farther. The Sun's energetic reach ends. This boundary is called the heliopause, and the vast bubble of solar influence it encloses, containing all the planets, all the moons, all the asteroids and comets and dwarf worlds of the known solar system, is called the heliosphere. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter true interstellar space. Voyager 2 followed in 2018. Both probes detected the crossing through changes in the particle environment around them, the solar wind particles dropping away and the density of interstellar particles increasing. The heliopause is not a wall. It is a pressure boundary, dynamic, asymmetric, pushed inward on the side facing the direction of the solar system's motion through the galaxy and stretched into a long tail behind. Beyond it, the Sun is just another star. We are not standing still. It is easy to think of the solar system as fixed, a stable arrangement of planets orbiting a stationary Sun at the center of everything we know. But the Sun is moving. It travels through the Milky Way at approximately 220 kilometers per second, following a broad orbit around the galactic center that takes between 225 and 250 million years to complete. As it moves, it carries everything with it, every planet, every moon, every comet and asteroid and drifting fragment of ice. At this moment, our solar system is passing through a region of space called the local interstellar cloud, a thin, diffuse concentration of gas and dust, roughly 30 light-years across. This cloud is itself embedded within a larger structure called the local bubble, a cavity in the interstellar medium believed to have been carved by ancient supernova explosions millions of years ago. As the solar system moves through this cloud, the heliosphere acts as a shield, deflecting interstellar particles and maintaining the relatively protected environment in which the planets reside. Changes in the density or composition of interstellar material through which the solar system passes may, over very long timescales, influence the shape of the heliosphere and potentially even the flux of cosmic rays reaching the inner planets. We are not sitting still in space. We are sailing, slowly, silently, through a thin galactic fog. And the fog through which we sail has been changing for as long as we have been moving through it. Activity is not reserved for planets. When we think of geological activity, volcanoes, geysers, shifting terrain, we tend to think of planets. Large bodies with hot interiors, driven by radioactive decay or residual formation heat, expressing their internal energy through surface processes. But several moons in the solar system are geologically active, and their activity in some cases rivals or exceeds anything found on the rocky planets. Io, orbiting Jupiter, is the most volcanically active body in the solar system. Its surface continuously reshaped by eruptions powered by tidal heating. Enceladus, orbiting Saturn, vents plumes of water and organic material from a subsurface ocean through fractures in its southern ice. Europa's surface shows evidence of a shifting ice shell, driven by the same tidal forces that warm its interior ocean. Ganymede likely harbors multiple layers of liquid water sandwiched between sheets of ice, warmed by a combination of tidal and radiogenic heating. Even Triton, Neptune's captured moon drifting in the cold outer solar system, shows signs of cryovolcanism, eruptions not of molten rock, but of nitrogen gas and icy material driven by the subtle warming of surface ice under the distant sun's light. These are not static, frozen worlds. They are restless. They are dynamic. They carry energy within them that expresses itself at the surface in forms ranging from sulfur eruptions to water plumes to shifting ice plains. The solar system's geology does not end at the planetary surfaces. It continues in quieter and stranger forms all the way out to the edges of the known system. Pluto is small, cold, and extraordinarily distant. At its average distance from the Sun, temperatures drop to nearly -230 degrees Celsius. It is, by most measures, one of the most inhospitable places in the solar system. And yet Pluto has an atmosphere. It is thin, far thinner than even the tenuous atmosphere of Mars, composed mostly of nitrogen, with traces of methane and carbon monoxide. Under normal circumstances, at Pluto's temperatures, these gases would simply freeze onto the surface and stay there. But Pluto's orbit is highly elliptical, and as it swings closer to the Sun during part of its 248-year journey, the surface warms just enough for those ices to sublimate, transitioning directly from solid to gas, lifting into the space above the surface and forming a hazy, layered atmosphere. When the New Horizons spacecraft flew past Pluto in 2015, it captured images of this atmosphere backlit by the distant Sun, a thin blue haze layered in concentric rings above the surface, delicate and unexpected and quietly beautiful. As Pluto moves away from the Sun again, that atmosphere collapses. The gases cool, freeze, and fall back to the surface as frost. The haze disappears. The sky goes dark and still. This cycle repeats every 248 years. An atmosphere that exists only in the warmest fraction of Pluto's long orbit. A brief frozen breath, exhaled and then withdrawn, over and over across geological time. At the center of the Sun, conditions exist that have no parallel anywhere on Earth. The temperature at the solar core exceeds 15 million degrees Celsius. The pressure is approximately 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways that bear no resemblance to anything in ordinary experience. Hydrogen atoms are stripped of their electrons entirely, moving as a dense, superheated plasma, and colliding with enough force and frequency that their nuclei occasionally fuse. It is this fusion, hydrogen nuclei combining to form helium, with a small amount of mass converted into energy in the process, that powers the Sun. Every second, the core converts approximately 600 million tons of hydrogen into helium. The energy released in that conversion is what eventually reaches Earth as sunlight, 8 minutes after leaving the solar surface. But the journey from core to surface is not quick. A photon of light generated in the solar core does not travel outward in a straight line. It is immediately absorbed and re-emitted, bouncing through the dense plasma in a random walk that may take anywhere from 10,000 to 100,000 years before the photon finally reaches the surface and escapes into space. The light warming your face on a summer afternoon may have begun its journey inside the sun before our species existed. Saturn's rings are famous. They are the first thing most people picture when they think of a ringed planet. Broad, bright, and immediately recognizable, even through a small telescope. But Saturn is not the only ringed planet in the solar system. Jupiter has rings, thin and faint. Neptune has rings, dark and narrow. And Uranus has rings, 13 of them, discovered not by direct observation, but by accident. In 1977, astronomers were using a technique called stellar occultation to study Uranus's atmosphere, watching the light from a distant star dim as Uranus passed in front of it. Before the planet itself blocked the star, the light dipped unexpectedly, multiple times on both sides of the planet. Something around Uranus was interrupting the starlight. Those interruptions were the rings. Unlike Saturn's broad, icy bands, Uranus's rings are narrow and dark, composed of particles that reflect very little light, making them nearly invisible in ordinary observations. Some of the rings are remarkably sharp-edged, their boundaries maintained by small shepherd moons whose gravity confines the ring material into tight, defined bands. Because of Uranus's extreme axial tilt, the rings orbit in alignment with the planet's equator, meaning they appear nearly vertical when viewed from certain angles, encircling a planet lying on its side. 13 dark bands circling a tilted world. Subtle, shadowy, and easy to overlook. But there. For centuries, Mercury's orbit presented a problem that no one could fully explain. Astronomers had known since the 1800s that Mercury's perihelion, its closest point to the Sun, shifts slightly with each orbit. The planet's elliptical path slowly rotates around the Sun over time, a phenomenon known as orbital precession. Most of this precession could be accounted for by the gravitational influences of the other planets. But a small residual amount, about 43 arc-seconds per century, stubbornly refused to fit the predictions of Newtonian gravity. It was a tiny discrepancy, almost negligible. But in science, tiny discrepancies that refuse to go away are often pointing at something important. In 1915, Albert Einstein published his general theory of relativity, a new framework for understanding gravity, not as a force acting between masses, but as a curvature of space-time caused by the presence of mass and energy. Near a massive object like the Sun, space-time curves significantly, and the paths of objects moving through it are subtly altered. When Einstein applied his new theory to Mercury's orbit, the prediction matched the observation exactly. The 43 arc-seconds per century that Newtonian physics could not account for emerged naturally from the mathematics of general relativity. It was one of the first experimental confirmations of a theory that would go on to reshape our understanding of the universe. And it was written in the orbit of a small, scorched planet circling close to the Sun. Twice a day, in most parts of the world, the ocean rises. And twice a day it falls. This rhythm, so familiar, so constant, so woven into the life of every coastal community in human history, is written by the Moon. The Moon's gravity pulls on everything on Earth, including the oceans. On the side of Earth facing the Moon, that gravitational pull is slightly stronger than average, drawing the ocean water outward into a bulge. On the opposite side of Earth, the moon's pull is slightly weaker than average, and the water there bulges outward in the other direction due to inertia. As Earth rotates beneath these two bulges, most coastal locations pass through them twice each day, experiencing 2 high tides and 2 low tides in approximately 24 hours. The Sun also contributes to tidal forces, though its effect is smaller than the Moon's despite its far greater mass, because tidal force depends on the difference in gravitational pull across a body, and the Moon, being so much closer, produces a larger difference. When the Sun and Moon align, their tidal forces combine to produce higher high tides and lower low tides, called spring tides. When they are at right angles, their effects partially cancel, producing the gentler neap tides. The Moon's tidal influence extends beyond the oceans. It subtly flexes Earth's crust, influences the planet's rotation, and has, over billions of years, gradually slowed the length of our day. A silent gravitational conversation carried on between Earth and its moon, every hour of every day. Beyond Neptune, in the cold outer reaches of the solar system, something may be waiting to be found. Astronomers studying the orbits of distant Kuiper Belt objects, small icy bodies moving through the outer solar system, noticed something unusual. Several of these objects follow orbits that are clustered together in space in a way that seems statistically unlikely to have occurred by chance. Their orbits are tilted and elongated in similar directions, as if something large and distant is gravitationally shepherding them. The leading explanation is the existence of an undiscovered planet, sometimes referred to as Planet 9, with a mass estimated at several times that of Earth, orbiting the Sun at an enormous distance. At that distance, it would take between 10,000 and 20,000 years to complete a single orbit, moving so slowly and reflecting so little sunlight that current telescopes have not yet been able to detect it directly. The evidence for Planet 9 remains indirect. The orbital clustering of Kuiper Belt objects is suggestive but not conclusive. Some researchers argue that observational biases in how those objects were discovered could explain the pattern without requiring a hidden planet. But the search continues. Several survey telescopes are systematically scanning the outer solar system, looking for a slow-moving point of light that does not match any known object. If Planet 9 exists, its discovery would reshape our understanding of the solar system's outer architecture and raise new questions about how and where it formed. Of Jupiter's 4 large Galilean moons, Callisto is the outermost. It orbits beyond the most intense regions of Jupiter's radiation belts, moving through a comparatively quieter region of space. Its surface is ancient and heavily cratered, one of the most heavily cratered surfaces in the entire solar system, showing no signs of the geological resurfacing that has erased impact records on Io, Europa, and Ganymede. From the outside, Callisto appears to be the most geologically dead of the 4. A frozen, unchanging record of 4 billion years of impacts, preserved in ice and rock. But beneath that ancient surface, something unexpected may exist. When the Galileo spacecraft flew past Callisto in the late 1990s, it measured subtle variations in the Moon's magnetic field, variations consistent with the presence of a conductive layer beneath the surface. The most straightforward explanation for such a layer is a subsurface ocean of salty liquid water, similar to those suspected beneath Europa and Ganymede. If confirmed, this would be remarkable. Callisto shows none of the tidal heating that drives the internal activity of the other Galilean moons. Whatever warmth maintains a liquid layer beneath its surface would have to come from a different source, perhaps residual heat from formation or the insulating properties of the ice above. A world that looks entirely static on the outside, possibly not static at all within. Mercury is the closest planet to the Sun. It receives more solar radiation per unit area than any other planet. Its dayside surface reaches temperatures above 400 degrees Celsius. By any intuitive reasoning, it should be the hottest planet in the solar system. It is not. Venus, orbiting nearly twice as far from the Sun as Mercury, maintains an average surface temperature of approximately 465 degrees Celsius, hot enough to melt lead, hot enough to soften zinc, hot enough to make the surface glow faintly in infrared. Day and night, pole to equator, the temperature barely varies. The reason is Venus's atmosphere. Venus is wrapped in a dense blanket of carbon dioxide, nearly 90 times thicker than Earth's atmosphere, with clouds of sulfuric acid suspended in its upper layers. This atmosphere is extraordinarily efficient at trapping heat. Sunlight passes through it relatively easily on the way in, but the infrared radiation that the surface tries to radiate back into space cannot escape. It is absorbed and re-radiated back downward again and again in a runaway greenhouse effect that has had billions of years to intensify. Mercury, with virtually no atmosphere, loses its heat rapidly. Its night side cools to nearly negative 200 degrees. The heat simply escapes into space. Venus holds every degree it ever receives. And in holding it, it has become the hottest surface in the solar system. Proximity to the Sun matters. But what you do with the heat you receive matters more. Saturn's rings are among the most studied structures in the solar system. And the more closely they are examined, the more intricate they become. The rings are composed overwhelmingly of water ice, particles ranging from microscopic grains to irregular chunks several meters across, each one independently orbiting Saturn in the same flat plane. It is this ice that gives the rings their remarkable reflectivity, making them one of the brightest features in the solar system when viewed from the right angle. Freshwater ice reflects sunlight with extraordinary efficiency, and the rings are, in most regions, remarkably clean. Within the rings, structure emerges at every scale. There are broad divisions, gaps in the ring material created by gravitational resonances with Saturn's moons, the most prominent being the Cassini division, a gap nearly 5,000 kilometers wide. Within the main rings, there are narrower ringlets, wave patterns, and braided structures. Some gaps are maintained by small moons, Pan and Daphnis, that orbit within the rings themselves, their gravity carving clear lanes through the surrounding ice. The edges of these moon-maintained gaps are not smooth. They are scalloped, rippled into waves by the gravitational wake of the moon passing through, like the bow wave of a ship moving through water. At the scale of individual particles, the rings are in constant slow collision, fragments bumping gently against one another, exchanging momentum, redistributing material in patterns governed by orbital mechanics, and the subtle but persistent influence of Saturn's oblateness. What looks, from a distance, like a simple flat disk is up close a vast and intricate system, dynamic, structured, and ceaselessly in motion. In the asteroid belt between Mars and Jupiter, most objects are irregular fragments, rocky, cratered, and shaped by whatever collisions formed and subsequently damaged them. They range from boulders to bodies hundreds of kilometers across, but almost none of them are large enough for gravity to have pulled them into a spherical shape. Ceres is different. With a diameter of approximately 945 kilometers, Ceres is the largest object in the asteroid belt, large enough that its own gravity has shaped it into a roughly spherical form. This makes it, by the International Astronomical Union's definition, a dwarf planet. It is the only dwarf planet located in the inner solar system, and the only one that has been visited by a dedicated spacecraft. NASA's Dawn mission arrived at Ceres in 2015, and what it found was more complex than expected. The surface was dotted with numerous bright spots, highly reflective patches that stood out starkly against the darker surrounding terrain. Analysis revealed these spots to be deposits of sodium carbonate, a salt likely left behind by the evaporation of briny water that had welled up from beneath the surface. This was significant. It suggested that Ceres is not simply a relic of early solar system formation, frozen and inert, but a world with some degree of ongoing or recent geological activity. Possibly a subsurface reservoir of water or mud. Possibly cryovolcanism. Not quite an asteroid. Not quite a planet. Something in between, a hybrid world carrying the chemistry of something larger than it became. The color of Mars is not arbitrary. The planet's distinctive reddish hue, visible even to the naked eye from Earth, bright enough that ancient astronomers named it after the god of war for its bloody appearance, comes from a specific chemical compound coating its surface. Iron oxide.